Welcome to the first session of the uh, of today, which is the last day of this symposium. Um we are lucky to have a very eminent chairperson for this for today's session, Professor Tarun Souradeep, who works in the area of cosmology and gravity, and he is a chair physics of IISER Pune. Over to you, Tarun, to conduct the
Thank you.
proceedings.
Thank you for this opportunity. So let me begin by paying my tribute to the memory of Professor Chitre, who was a doyen of Indian science and an astrophysicist of international acclaim. I have been very fortunate to benefit from interactions and very encouraging and inspiring interactions with him from my very early research days when I just started in IUCAA, early 90s. And what I found really amazing is he would egg you on always to reach further and dig deeper. So even as a faculty member, I always found that he would sort of, appreciate what you've done, but always point to the fact that you could do much better. And that always keeps you going. And not surprisingly, he was also an educationist at heart, and CEBS and the generation of scientists it will produce would stand a glowing tribute to his immense contributions to Indian science. So now let me move to this. I feel immensely privileged and honored to introduce whom I consider a living legend of gravitational science, Professor Kip Thorne. He is, of course, a recipient of the Nobel Prize in 2017 for his crucial role in the 4-decade-long quest to detect gravitational waves. And he was always convinced that it will open a new window to the universe. And not only was he convinced, he kept an entire nation convinced, then funding agencies convinced that this was a goal worth. And I think that's amazing. So the Nobel Prize is, of course, just a centerpiece jewel to many, many accolades and awards he has received. And I won't even try to list even the most prominent ones, anything that you can think of. What is unique is he pioneered new ways of how to think about the nature of space-time and dynamics. So what he loves to call geometrodynamics. And each of them had an unique appeal to physical intuition. Besides, of course, revealing deep scientific truth. And I think every practitioner in the field has been touched by him in some form or the other. If not anything, they would have studied gravitation from MTW. I know Sanved would have done that, surely. So geometrodynamics has been his lifelong fascination, as is apparent in the title of his PhD thesis with Professor John Wheeler in 1965. That was titled Geometrodynamics of Cylindrical Systems. He did his bachelor's from Caltech, master's at Princeton, and has been a faculty of Caltech since 1967, where he's currently the Feynman Professor of Theoretical Physics. As you'll soon experience, Kip has a remarkable gift of communicating science. He has the ability to make even grown-up researchers relive the thrill of their young days. And I personally remember attending his 2009 IAP colloquium and really feeling really convinced and vindicated about our nascent thoughts about launching an effort in India on building a gravitational wave detector that he then supported and also lent his strong support in later years. Just finally, I should mention that I first met him in 1993 as a final year graduate student on my grand tour. He hosted my Caltech seminar, and I should mention, Kip, that I still treasure his appreciation when I fixed up the OHP projector with some what is called Indian jugaad or a hack. So here's Professor Kip Thorne on geometrodynamics and its growing prominence in astrophysics. Over to you, Kip.
Thank you very much, Tarun. I must apologize that I'm in rural America in a forest in Oregon. And in rural America, the internet connections are not very stable. So if I disappear, I won't be gone longer than 3 minutes, hopefully much less. And if we're lucky, I won't disappear. I'm going to share my screen. Go and bring up my, okay, good. Can you see my screen?
Yes, we can.
Good. So I had the great pleasure of collaborating with Kumar Chitre and Jim Hartle in the early 1970s when Kumar was a postdoc at Caltech and I was a young professor. Pulsars had recently been discovered and identified as rotating neutron stars. So we embarked together on the theory of pulsations of rotating neutron stars, and we had great fun and some success, thanks largely to Kumar. So it's an honor and pleasure to participate in this memorial symposium for him, that is for Professor Chitre, as he came to be called as he moved forward into his outstanding career. In this lecture, I shall describe the concepts and status of geometrodynamics. That is the nonlinear dynamics of curved space-time. And near the end, I'll address the question in the title, will geometrodynamics become a branch of astrophysics? This story begins with John Wheeler, who coined the word geometrodynamics and the concepts of the nonlinear dynamics of curved space-time 60 years ago. This is a photograph that I took. It's blown up hugely because I took it from the back of the lecture room, of John lecturing a few years after he coined the concept, but lecturing about geometrodynamics. You see this diagram of a black hole as seen from a higher dimension. In that era, he urged his students and his colleagues to explore the nonlinear dynamics of curved space-time. There should be wonderful and amazing phenomena occur there. We tried for 4 decades and were very frustrated from 1958 to 1998. The problem was analytic techniques gave little progress. It was just too hard when you're in a situation where space-time was not only strongly curved, but also highly dynamical. John Wheeler foresaw this, and so from the outset in the 1950s, he encouraged his students and colleagues to develop numerical relativity. So Einstein's equations could be solved on computers and one could deal with generic situations like geometrodynamics. It took 4 decades for numerical relativity to reach fruition. It neared fruition in 2000, and it took 15 more years to near maturity, about 2014, which is barely in time for LIGO's use of it. But already then in the late 1990s, as it was nearing fruition, we began to get insights into geometrodynamics, thanks to a combination of numerical and analytical relativity. And in this lecture, what I'm going to do is tell you about what we've learned, basically an overview of what we've learned through numerical and analytical relativity. And then at the end, I'll ask about the connection between this and astrophysics. I'm going to describe 4 arenas for geometrodynamics. First, geometrodynamics near singularities. And there we will see that the warped space-time, curved space-time is governed by chaotic maps as similar to what occurs in the onset of turbulence in fluids. I'll talk briefly about geometrodynamics in the nonlinear self-coupling of gravitational waves in what is called critical collapse. And there we will see critical behavior and scaling, nonlinear phenomena that are familiar from phase transitions in condensed matter physics. Then I will talk about geometrodynamics in the context of colliding black holes. There we will see veritable storms in the geometry of space and time, analogous to a storm at sea, storms that involve a coupling of what we call frame drag vortices of twisting space to tidal tendencies of stretching space. These are physical structures made of warped space-time that are attached to black holes. And then finally, I'll talk about gravitational wave observations of geometrodynamics and the connection to astrophysics. So that's where I'm going. Let me begin with geometrodynamics near the singularities, and I'll go way back to Oppenheimer and his student Hartland Snyder in 1939, who, as I think we all know, studied the gravitational collapse of a spherical ball of dust to form a singularity surrounded by what we now know as a black hole horizon. And the tidal forces that stretch and squeeze a person that is near the singularity, and those tidal forces are one way of characterizing the space-time in the vicinity of the singularity, and to characterize the nonlinear dynamics of curved space-time near the singularity. So the period of 1939 to the 1960s, the question was continually asked, do singularities really form in nature? And Lifshitz and Kalatnikov in Moscow gave a resounding answer, no, they do not form generically in nature in the 1960s. And they memorialized this, I mean, they published their proof, and they memorialized their proof in the Classical Theory of Fields, their famous textbook, in a section called The Absence of Singularities in the General Cosmological Solution. By general cosmological solution, they really meant in generic solutions of the Einstein field equations. So it was a shock to Lifshitz and Kalatnikov when in 1965, Roger Penrose at a conference in London, which was attended by Kalatnikov, he said, on the contrary, there are generic singularities that are unavoidable, in particular inside black holes. He used techniques of differential topology to prove singularity theorems, and he showed that time-like world lines necessarily end inside a black hole. But he could not give us any information about the geometrodynamics, the details of the warped space-time near the singularity. From 65 to 69, there was great consternation, very great unhappiness in Moscow. And finally, in 1969, Walensky, Kalatnikov, and Lifshitz found the error in their analysis and in their chapter in the Classical Theory of Fields. And they, for the first time, elucidated the geometrodynamics near a singularity. This is a photo, that's a picture of Roger Penrose.
Professor Kip?
I think he had told us that he may get disconnected. So I request the audience to kindly wait until he reconnects. It may take a minute or two. I think he has joined back.
Okay.
Hi,
Okay, can you
Professor
see?
Kip, can you hear us?
Yes. Can you hear me?
We can hear you.
Yeah.
Okay, I'm on a different internet provider, and let's hope this one is better. Carolee, let me just ask my wife to, just one moment. Carolee? Carolee? Carolee, I lost the internet. Okay. Okay, my apologies. I think this provider may be better. So I'm going to share my screen once more. Share. And I will bring up my presentation once more. Okay, can you now see this?
Yes, yes, we can. We actually lost you when you were on the previous slide.
Okay. Okay, so Roger Penrose contradicted our Russian colleagues with regard to generic singularities in 1965, using techniques of differential topology, which he brought into relativity for the first time. He showed that time-like whirl lines end inside a black hole, so there must be a singularity in there. But he could not give us any information about the details of the singularity, the details of the dynamics of curved space-time near it. This caused great unhappiness in Moscow, great embarrassment, because the relativity theorists throughout the West, at least, could see absolutely Roger was right. His analysis was very crystal clear, and the approximate analysis of the Russians was not so clear. It could have failed in many ways. And so they struggled for 4 years. And finally in '69, Belinsky, who is now a student of Kalatnikov's, together with Kalatnikov and Lifshitz, found the error in their analysis, the error in the classical theory of fields. And this is a photograph taken a year or two after that of dinner at Kalatnikov's home. This is Kalatnikov, Belinsky, the student, Lifshitz, the famous Yevgeny Lifshitz of Landau and Lifshitz fame, John Wheeler, myself, Kalatnikov's wife and daughter. And then from '69 to '71, they developed in great detail what's been called the BKL approximate analysis of the generic singularity. And what they found is that near a generic space-like singularity, that if you have several freely falling observers, as they near the singularity, they lose causal contact with each other. There's a spatial decoupling of the Einstein equations. They can be converted from partial differential equations into ordinary differential equations in time, but independent evolution as seen by each observer nearing the singularity. The temporal dynamics as seen by each observer is that of so-called mixed master, first discovered by Misner and by Belinsky and Kalatnikov in homogeneous cosmologies, but here it is in an inhomogeneous form. They found that matter has negligible influence on this, and they focused on the stretching and squeezing, say, of freely falling observers, for example, produced by a tidal field. And by the tidal field Newtonian regime, the tidal field is the usual tidal field. That's the gradient of the gravitational acceleration, or minus the double gradient of the Newtonian potential. And I'm going to focus on this tidal field and give you a little bit of mathematics as we go along, but not very much. And so the key point is that if you have two freely falling particles separated by a separation vector c, there is a relative acceleration of the particle at this location, p, relative to the freely falling particle at q. That relative acceleration is just the scalar product of the tidal field with a separation vector. And so that is the standard tidal force or tidal acceleration that, for example, raises the tides on the Earth's oceans when the tidal field is due to the moon. The key thing that they found is near the singularity, and this is familiar to many of you, that if the person falling into the singularity gets alternately stretched along one direction and squeezed to the sides, then stretched to the sides and squeezed vertically, and that oscillates over and over again in a pattern that is actually chaotic. So if I plot stretch up and squeeze down, in the east-west direction, there will be a squeeze, 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 and then suddenly a change at the end of what they called an era, and then stretch, squeeze, stretch, squeeze. So there's a huge transition at the end of an era, and these are called cycles. In the up-down direction, there's a stretch, squeeze, stretch, squeeze, stretch, squeeze. And in the east-west, and similarly in the north-south direction, the opposite behavior. So this basically chaotic behavior, governed in fact by a chaotic mathematical map, that goes on and on and on with in principle, if the quantum theory never entered in an infinite number of cycles and eras of this chaotic behavior. This is really fascinating to see chaos, a formal mathematical chaos coming out of cosmology. There was great skepticism of this claim in the West because the proof involved perturbation theory and involved combining and matching together perturbation theory in various regimes. And so it came to be called in the West the BKL conjecture, quote, proved by, quote, heuristic arguments. And it was really rather much disbelieved in the West, at least by most people. I think I tended to have a faith in the analysis, but I never had the level of rigor in my approach to physics that some of my other colleagues had. And so as soon as numerical relativity became sufficiently mature, there was a program set up to test this BKL conjecture via numerical simulations. And the person who really pulled it off in the end most successfully was Garfinkel at Oakland University. And what he found was a confirmation of what had been claimed by B, K, and L, aside from some spikes that were missed in the stretching and squeezing. But aside from this very minor difference, it was basically as had been laid out by Belinsky, Coulomb, and Calvin Lifshitz. If we go inside black holes, then what we expect is occurring is that there is a BKL singularity, because these things are generic, down at the center of the black hole. But through perturbation, other perturbation analyses, we have found that it's been found that there are two other singularities inside a black hole. And this is discussed in the movie Interstellar that I was involved in a little bit. And in my book, The Science of Interstellar, I draw this picture. Here you have Cooper in the movie Interstellar has fallen into the black hole. This is an embedding diagram for the black hole. The black hole horizon is there, headed toward the singularity. And time is so screwed up inside the black hole that everything that falls into the black hole afterwards comes crashing down in a fraction of a second on top of Cooper in the form of a shock wave, what I like to call an infalling singularity. But the people who first discovered this were Eric Poisson and Werner Israel, and they call it a mass inflation singularity. And that is a singularity that arises so quickly that the double time integral of the stretching and squeezing of the Riemann tensor, the double time integral is finite. And so it is a gentle singularity in the sense that the total stretch and squeeze approaching that singularity is not infinite. It's really quite remarkable. And Donald Marolf and Amos Ori in 2012 showed that similarly, everything that among everything that fell into the black hole before Cooper, some portion scatters back up and comes up in a very thin singular structure that is an outflying singularity, or they called it a shock singularity, which again is a singularity that whose net stretch and squeeze when you hit the singularity is still finite. And so just what that means for the fate of somebody who hits the singularity is not completely clear, even after all these years. Now, that is what we think is going on. I think that's what the community of physicists who've studied this think is going on. But computer simulations are badly needed to be sure that that's what's going on, because this, again, is based on perturbation theory and patching together perturbations in various regimes. And in fact, these simulations are beginning to get underway. For example, Franz Pretorius at Princeton has embarked on at the beginning of this. Now, let me turn to geometrodynamics in imploding waves. And I'm going to begin with an analysis by Matthew Choptuik in 1993, not with imploding gravitational waves, which is where I'm going in a moment, but analysis of imploding spherical scalar waves. And what he found is if you take a scalar wave And I've removed one spatial dimension from this diagram. So I'm showing just two spatial dimensions and then plotting upward the strength of the scalar field. And you pick any kind of a shape for the scalar wave you might wish, but focus on the actual amplitude of the scalar wave and gradually change the amplitude of the scalar wave to see what happens for one amplitude after another after another. If the amplitude is sufficiently high, then the energy in the scalar wave basically generates space-time curvature that produces a black hole. It's just the energy in the scalar field gravitating, producing the black hole. And if you have an amplitude that differs by some small amount from the critical amplitude at which a black hole first forms, then the mass of the black hole that forms goes as the actual amplitude minus the critical amplitude to some critical exponent beta, which is found through numerical simulations by Matt Choptuik to be 0.374. And if the amplitude is a little less than this critical amplitude, then the wave comes in, it disperses, and the maximum radius of curvature that is created before it disperses scales in the same way with the same power, beta of 0.374. This is the same kind of behavior as you see in phase transitions in condensed matter physics. And if you have an amplitude that's precisely equal to the critical amplitude, then the scalar wave comes in and it undergoes a sort of an organized boiling or frothing with the structure of something like this that is discretely self-similar as it goes in and in and in, forming a tiny naked singularity at the end, and with the waves coming out, discretely self-similar waves coming out. So this is really quite a remarkable and strange behavior that Matt discovered, and that in fact has been shown to occur for many other systems with a gravitational collapse. And so Andrew Abrahams and Chuck Evans in 1993, then much higher accuracy, Yevgeny Sorkin in 2011, did the same problem with gravitational waves, actually symmetric, not spherical, because if you have a spherical system, you can't have a gravitational waves cannot exist in a precisely spherical form. So it's actually symmetric. But they found with gravitational waves, the waves self-coupling via the nonlinear Einstein equations led to precisely the same kind of a behavior with, to the accuracy of the numerical work, precisely the same critical exponent between whether a black hole forms and whether you get waves that disperse. And again, and they saw moderately strong evidence for discretely self-similar frothing. Now, numerical studies of this are still in their infancy, and there's a great richness that remains to be uncovered. But what we see now, we've seen in this case of nonlinear interaction of waves with themselves and with space-time curvature, we have seen critical behavior in scaling as in nonlinear phenomena in condensed matter physics, phase transitions. And for near singularities, we have seen chaotic behavior, the same sort that occurs in the onset of turbulence in a fluid. And so it's really been quite exciting to see that general relativity, through its just own natural nonlinearities, produces the same kinds of fascinating behaviors as in other areas of nonlinear physics. So now let me turn to the most interesting case, that of black holes. And I'll remind you, of course, that black holes are made from warped space-time. So if we make an embedding diagram of the spatial slice through a Kerr black hole, the shape of the, as I think we're all aware, the shape of space looks like a trumpet horn. The slowing of time, which is described by the so-called lapse function, time slows to a halt at the horizon. The horizon looks like a circle. It's really a flattened sphere when you restore the missing dimension. Where it's yellow, time is flowing at 10% the normal rate out back here on Earth, say, and down here at the horizon, it slows to a halt. And the arrows show the negative of the shift function, which can be thought of as the angular velocity of dragging a space into a whirling motion. And that's a very rigorous way, in fact, of talking about what's going on. And so the space-time geometry of a quiescent black hole outside the horizon is all contained in this diagram. This geometry of space and the shape of this surface, the slowing of time or the lapse function in the color coding, and the dragging of space into whirling motion, or the so-called shift function in the white arrows. Now, what happens when two black holes collide? Well, it was a pretty good guess, and this is a drawing from that guess, back around in the early 1980s when we began to work on a serious sort of way on LIGO. The two black holes orbiting each other would spiral together, collide, and merge, and would produce gravitational waves traveling out into the universe. And so we use this to, in selling LIGO to funding committees and to the National Science Foundation, just this little diagram. We now understand, in fact, thanks to numerical relativity, to pin down the exact numerical values. We understand that the power output in gravitational waves is 50 times the luminosity of all the stars in the universe during the collision. This is just incredible. But the total energy that comes out is a few percent of the mass of the black hole binary, because the duration of the collision scales with the mass, gets shorter at smaller masses, and the power output remains the same. So the fractional remains fixed at 50 universe luminosities. So the fractional energy loss is also fixed. It's a few percent of the mass of the black hole binary. No electromagnetic waves are emitted whatsoever, of course, except somehow I lost my, just a minute. I don't know where that went. Just give me a moment. Are you still there?
Yes, yes, we're still there. There's no problem.
Okay. Weird. Okay. Okay. There's no electromagnetic waves emitted except possibly from disturbed accretion disks. The key thing that I want to focus on is that the details of the collision, that is the geometrodynamics, are encoded in the gravitational waves waveforms. So I wrote down then, back in the early 1980s, a possible waveform, this coming from the in-spiral, that coming from the collision, where you would have very interesting nonlinear dynamics, and this coming from the vibrational ring down of the final black hole. And this was my speculation. Finally, just in time for LIGO's first detection, the numerical relativity community was able to simulate generic black hole collisions from generic black hole binaries. And this is a simulation of the collision of that resulted in the first gravitational wave signal seen by LIGO. It's done by what's called the SXS collaboration that was put together by Sol Tukolsky, involved Cornell, Caltech, CETA at the time of this simulation, Cal State Fullerton, Oberlin, Washington State University. So a number of different universities around the US and Canada. And what I'm showing you now is the depiction of the spatial metric, the geometry of space during the collision. And I'm going to put this in slow motion as the two black holes approach each other. And you can watch at the moment when this splashes up to its maximum height, that's when the horizons perfectly merge. The color coding again is the slowing of time. That's the moment of collision. I'm going to return to it later in my lecture. And the final black hole vibrates and sends out gravitational waves. There's a problem with this, that the too little of the space-time geometry is depicted in this way. And so in 2011, together with a set of students, former graduate students and postdocs of Yanbei Chen's and my research group at Caltech, we developed a way of visualizing the vacuum Riemann curvature tensor, the tensor which really describes the local curvature of space-time or warping of space-time. And I'm going to show you a little bit of the mathematics just to give you some sense of what underpins this. You don't need to follow the mathematics because I'm going to switch over to pictures in a couple of minutes. So in general relativity, one slice, and when doing numerical relativity, one slices space-time up into spatial hypersurfaces, which we can think of as a surface of constant time. And when you do that, if you're looking at the electromagnetic field tensor splits up into two pieces, the electric field and the magnetic field, which we visualize, for example, by means of field lines, such as these dipole field lines around the Earth. Similarly, the Riemann curvature tensor, which is the thing that describes the warping of space-time locally, it splits up into two parts, a part that has sometimes been called the electric or electric light part, which is really the tidal field that I talked about before, and a so-called magnetic type part, which I'll denote BJK. These are symmetric trace-free tensors, and they're related in a local inertial frame to the Riemann tensor in this way, where that's the Levi-Civita tensor. The tidal field describes tidal accelerations in just the manner that I described before. The frame drag field describes differential frame dragging, so that if you have two freely falling gyroscopes, one at Q and the other one at P, one at Q and one at P, or they can be accelerated gyroscopes as long as the forces to accelerate them are applied at their centers of mass. Then the gyroscope at P will have its spin axis precess. I'm sorry, I should be down here in this diagram. Will precess relative to the gyroscope at Q with a precessional angular velocity that is yet the scalar product of this frame drag field with the separation vector. So the tidal field, when you do this scalar product, gives you a relative acceleration of the two particles. The frame drag field with this scalar product gives you the differential precession, the precession of reference frames at one location relative to reference frames at the other location. Now, let me give you some sense of what this means in simple pictorial terms. Mathematically, we define tendex lines as the integral curves of eigenvectors of the tidal field. And that, in the case of the moon exerting a tidal force on the Earth and raising tides on the Earth's oceans, there are stretching tendex lines that stretch then anything that is in this vicinity, each and squeezing tendex lines that squeeze along that direction. Each tendex line has an eigenvalue, call it ENN, that's called its tendicity. And ENN is the relative acceleration between the head and the foot of my wife here, divided by her height. And so that is the measure of the stretching, is this tendicity. And the squeezing then along this direction. So the key thing that I'm going to focus on through the remainder of this talk is these tendex lines and similar vortex lines for the frame drag field. So just to give you some sense of this, for a spinning black hole, there are tendex lines that stretch, that come out like this, stretching tendex lines, as famously occurs stretching an astronaut who is falling into the black hole. But there strangely are squeezing tendex lines that come out of the North Pole, go around and come back down into the South Pole that would squeeze this astronaut or my wife along that direction. So this is a fascinating depiction of the Riemann tensor, that piece that has to do with stretching and squeezing around a spinning black hole. I'm going to focus primarily on a tendex or tendices, which are collections of tendex lines with very large tendicities, things that strongly stretch and strongly squeeze. Vortex lines outside a black hole are integral curves of eigenvectors of the frame drag field. And so sticking out of this black hole, out of the North Pole, there are vortex lines that if my wife is here and she has a gyroscope attached to her feet and one attached to her head, then her head sees the gyroscope and her feet twisting around due to differential precession in a counterclockwise direction. Her feet see her head twisting in a counterclockwise direction. So her body gets twisted. There is a counterclockwise twisting vortex sticking out of the black hole's North Pole. Sticking out of the black hole's South Pole, there's a clockwise twisting vortex. And I'm going to be focusing on these vortices in the rest of this lecture. Then here is, for a curved black hole, the vortex lines that twist clockwise, counterclockwise, and clockwise. And the key thing is, out of the North Pole, there's a counterclockwise vortex of twisting space. Out of the South Pole, a clockwise vortex of twisting space. So all the stuff I've done here mathematically is just to explain that there's really something very fundamental that underlies the story I'm going to tell you now. Physically, then, we can think of a black hole as having two strong tornadoes of twisting space sticking out of its two poles. And so we asked ourselves, having devised these ways to visualize the space-time curvature, the Riemann tensor, we asked ourselves what happens when two black holes collide, beginning, say, head on. And so I have these two black holes, one with its counterclockwise vortex up, clockwise vortex down. And this is an identical black hole, but oriented oppositely, clockwise vortex up and counterclockwise down. Here's what happens when they collide. Where it's green, there's very little vorticity, very little twisting. The vorticity is up here. I have screwed up the colors. This should have been blue, that should have been red. But the key point is that you wind up with four vortices of twisting space sticking out of a single black hole merged horizon. These two, one here and one on the backside, blue on the backside, came from that black hole. This one, blue and red on the backside, came from this black hole. And these vortices robustly retain their individuality, we find in simulations done with the XS team's computer code. And so now we'll watch what happens. I'm showing you only the color coding. That this is a clockwise vortex sticking out of the top of this hole, counterclockwise out of the bottom, counterclockwise out of the top, and clockwise out of the bottom. Now watch the blue clockwise vortex. When the collision occurs, the black hole oscillates, and what was blue has become red. What was red becomes blue. It's really quite remarkable. These vortices fight with each other and exchange directions of twist. They change their vorticities. What actually happens is shown here then. Whenever this black hole surface shows green everywhere, the vortex lines have popped off of the black hole. And when they pop off, so these are the blue vortex lines of the merged black hole, those are the red vortex lines. When they pop off, they embrace each other and form tori of twisting space. And so with each oscillation, a successive tori or donuts of twisting space go flying out at the speed of light away from the merged black hole. It's really quite remarkable. This is the essence of geometrodynamics in a head-on black hole collision. And it turns out that the so-called Bianchi identities of general relativity in a local Lorentz frame or freely falling frame look just like Maxwell's equations, except that E is a tidal field, it's a second-rank tensor, and B is the frame drag field. But the key thing is that the time derivative of the tidal field is the curl of frame drag field. Time derivative of the frame drag field is the curl of the tidal field. What this means is, just as in electromagnetism, these vortices of twisting space traveling outward at the speed of light generate tendencies that stretch and squeeze, that stretch along this long axis of the torus and squeeze around the short axis of the torus. And those then break this torus, which has then twisting vortices and stretching and squeezing tendencies, moves outward toward Earth, and it is a gravitational wave. That's the essence of a gravitational wave. It not only has stretching and squeezing, it also has twisting clockwise and counterclockwise, but we do not have adequate technology to see the twisting of space in a gravitational wave. So we only have adequate technology today to see the stretching and squeezing. What happens if this collision is a orbital collision? The two black holes then are orbiting around each other as they collide. Well, then what happens is that the vortices, the vortex lines that are sticking out of the black holes, they get just strung out behind like the water from a whirling sprinkler head. This is a precise depiction in the plane, in the orbital plane, a precise depiction of what happens to these vortex lines when the two black holes merge. They have this very interesting then pattern, like water from a whirling sprinkler. These vortices are attached to the black hole, and as they travel outward, they generate gravitational waves, just as in the head-on case. If you have the black holes that have just merged, so this is a horizon that has just merged, sticking out of the merger region, there turns out to be squeezing tendex lines, but sticking out of the ends of the black hole, there are stretching vortex lines. And as the black hole tumbles, as the merged black hole tumbles, these tendex lines sweep back like water from a whirling sprinkler head. And it's quite amazing that at late times, and this is just for some particular value of the black hole, of the final black hole spin, at late times for the final black hole, you have for the vortex generated gravitational waves, those that arise from twisting vorticities sticking out of the black hole, you have almost identically the same pattern where these are vortex lines, and these are vortices of twisting space, counterclockwise and clockwise, almost the same pattern as you have for the tendex generated gravitational waves, the tendencies of stretching and squeezing space. A near duality between the two sets of, between the two types of gravitational waves, vortex generated waves and tendex generated waves, but opposite parity. And what this means is that if you organize things appropriately, because of opposite parity, the vortex generated waves may reinforce going up the north pole of the merged black hole and may cancel each other going down the south pole of the merged black hole, or nearly cancel each other. And so the black hole is given a huge kick and heads off at many thousands of kilometers per second by this asymmetric gravitational wave emission that arises due to this near duality between the two types of waves, enabling them to superpose in a constructive way in one direction and destructive way in the other direction. Let me turn finally to gravitational wave observations of geometrodynamics. The challenge is from observed, let me just back up. The challenge is from observed binary black hole gravitational waveforms, how can we read off the geometrodynamics that occurs in the black hole collisions? That is the dynamics of these near zone vortices and tendencies. So here is one, the LIGO gravity wave detector that made the first observation and many other observations of black hole collisions. This is the one in Hanford, Washington. Of course, there will be one that we are looking forward very much in India in several years. The answer, how can we read off the geometrodynamics, is, well, by comparing the observed waveforms with the waveforms from simulations, we can identify the masses of the two black holes and their spins And then we can go back to the simulations for those particular masses and spins and look at the simulations dynamics. So here is an example of a 60 solar mass black hole and a 10 solar mass black hole with indicated spins and spin directions, gravitational waves going off toward Earth. You have two different waveforms because there are two polarizations. And by matching these waveforms to the simulations, adjusting, of course, the masses and spins of the black holes until you get a good match, you see then what are the masses and spins of the two initial black holes. Then you go back to the simulations and you see what was the geometrodynamics that occurred. LIGO and Virgo have now observed more than 40 black hole collisions. And there has been excellent agreement between the observed waves and the computer simulations and simulated waveforms. To what extent is this a verification of the geometrodynamics that I described? Is geometrodynamics now becoming part of astrophysics? To answer this question, let me go back to my speculation in 1984 as to what the gravitational waveforms would look like. During the in-spiral, you have a gradually rising amplitude and shortening gravitational wave period. During the collision, I was expecting and hoping for a lot of very interesting dynamical behavior corresponding to the geometrodynamics of the collision era. And then finally, when you get close to the final black hole with energy from the collision having been carried off in gravitational waves, a final ring down, a damped sinusoid for the gravitational waves. The actual waveforms are far simpler, and this is very sad. For example, for that first gravitational wave that was discovered, GW 150914, came in on the September 14th of 2015. Here is the merger era, the merger epoch, which I had hoped would look something like that. And it doesn't look at all like that. It is just really, really simple. What's going on here? Well, it took 5 years for people to really smoke out what's going on really clearly. And this was smoked out by Saul Tucholsky and his collaborators on the SXS collaboration, numerical relativity. And they figured it out in 2000. And I'll give you a reference, a paper on GRQC that I think may not yet be published, should be published soon. Let me remind you, this is the shape of space as seen in that embedding diagram at the moment of collision. And the key thing that they found in their computer simulations is that if you draw a circle around or a surface around the merging black holes, that has a size about 1.5 times the radius of the final merged black hole. This has all of the wild dynamics inside of it, and almost everything in terms of the distortions for space and time inside here turns into gravitational waves that go down the black hole. And the stuff that comes out that we see with LIGO and Virgo, it's almost all coming from outside this circle. And at the moment of collision, outside this circle, the space-time geometry is almost that of the final black hole with just small perturbations. So near horizon disturbances go down the hole. The waves come primarily from greater than or order 1.5 horizon radii, where at the moment of collision, space is already almost out of the final black hole. And so it turns out that from the moment of collision onward, the moment of collision is where the amplitude of these waves is a maximum. Already at that point, the gravitational waves are almost precisely a superposition of two normal modes of vibration, or they're called quasi-normal modes of vibration of the final black hole, everything from here on. And that was simply not understood until late last year. And by measuring the frequency and the decay time for both of these normal modes, Tucholsky and his students and postdocs, colleagues, Maximiliano Isi, Will Farr, Matt Geisler, and Mark Scheel, they were able to infer the final black hole's mass and angular momentum independently of what we knew already from the gravitational wave observations about the initial black hole's mass and angular momentum. They were able to test the no-hair theorem, that the final black hole really is a Kerr black hole. There's not much distortion away from a Kerr black hole. And they were able to confirm Stephen Hawking's second law of black hole mechanics, the area increase theorem, to an accuracy of 97% confidence, which is really quite remarkable. And that's with the very first gravitational wave signal that was ever seen. There is actually hope. I mean, it's quite disappointing that these merger gravitational waves are not any more interesting than this. There is hope for more rich observations of geometrodynamics, as was found by Huan Yang, Aaron Zimmerman, and Louis Lehner through a combination of numerical relativity and analytical relativity calculations. It's back in 2015. When you spin the final black hole up, just imagine a sequence of final black holes that have various spins. If you can find a final black hole after the merge that has a spin that is close to the maximum spin that we expect to see in nature, 0.998 for so-called A over M in relativist jargon, you get a long neck in the geometry of space, and they found that because of that long neck, the perturbations of this final black hole get trapped inside this neck long enough that there can be nonlinear mode-mode coupling between the normal, quasi-normal modes of this black hole, long enough and nonlinear mode-mode coupling that gives rise to what's called two-dimensional turbulence, chaotic behavior, a two-dimensional analog of three-dimensional turbulence. And there is hope. It's not obvious that we will ever see this, but there is real hope that we may see this, may see the spectrum of turbulence, of two-dimensional turbulence come off from the final black hole collision, when the final black hole, from the black hole collision, when the final black hole is spinning very rapidly. But nevertheless, geometrodynamics has not yet seeped into the consciousness of astrophysicists. It plays no role in astrophysicists' thinking these days. It plays no explicit role in LIGO data analysis. So far, it is almost entirely just a beautiful playground for theorists like me, even though it underlies black hole collisions, even though it is the essence of the black hole collisions. Nevertheless, is not really a part of a tool or even hardly part of the language of working astrophysicists. And I suspect that for geometrodynamics to become a robust part of astrophysics, it will require seeing lots of geometrodynamical richness in gravitational wave data. And this may come with LISA, Laser Interferometer Space Antenna, which will have, for binary black hole collisions, we will see signal to noise ratios as large as 10,000 or maybe even higher. And with those huge signal to noise ratios, we may begin to see really interesting, rich geometrodynamical phenomena in the actual waveforms. So I thank you for listening, giving me this opportunity to talk about my favorite subject in physics these days.
Thank you, Kip. As usual, it's an amazingly rich talk and also very contemporary. I mean, it's something that you are currently thinking of, and I should say, I mean, of course, everyone must be saying this to you, but you get energized listening to you. I mean, really, thank you. There are a few questions, and I think we could take a few questions. From Samik Mitra from IIT Guwahati asks, when a prograde and a retrograde black hole collides, what happens to the effective spin of the merged black hole? And how do you explain momentum conservation, angular momentum conservation?
So let's just talk about the head-on collision that I talked about. So where we had a head-on collision of two black holes, they're spinning in opposite directions, they're identical. And so the net and its head-on collision equal and opposite spins. So the final black hole is going to have zero net spin in that case. And so it's a Schwarzschild black hole. And that's what you wind up with in this case, where you get these rings or tori of twisting space traveling outward and generating tendencies of stretching and squeezing space. In the more generic situation of orbital collision, where these vortex lines and tendex lines sweep back outward like water from a whirling sprinkler. In that case, then the angular momentum of the final black hole is determined by a combination of the spins of the initial black holes and the orbital angular momentum as the holes begin to collide. And you can deduce it by computer simulations, but remarkably, thanks to these insights of Tucholsky and his colleagues, you can actually measure the final black hole spin through looking at the normal modes of the that are emitted by it. What happens then to conservation of angular momentum? Well, it's there is a fundamental conservation law in general relativity which says that the angular momentum of the final black hole minus and that's a spin angular momentum, minus the angular momenta of the initial of the spins of the two initial black holes and their orbital angular momentum. That's just the angular momentum that goes off in the gravitational waves. There's a standard conservation law, just like there would be in Newtonian theory. And that's one of the beautiful things in general relativity. There are subtleties about the concept of angular momentum in general relativity, but the subtleties do not get in the way of the usual conservation law for angular momentum.
Okay, Kip, thanks. So let me take another question, and I'm told by the organizers that they'll send you a set of select questions, and if you could take your time and reply to them at some point, that would be very well appreciated, because there are lots of questions. And so one of them is from Professor Vivek Datar, who still recently was leading the Indian Neutrino Observatory. Is there any way to distinguish between a black hole and a compact super heavy object, since they're presumably indistinguishable beyond the event horizon?
So, of course, a black hole has an event horizon, and anything with an event horizon is regarded as a black hole. Whatever is going on inside the horizon has no causal influence on the exterior. So all we know about is the horizon and the exterior. And so once a horizon has formed, and after all the perturbations have gone away in the form of gravitational waves or to infinity or down the horizon, you're left with a spinning Kerr black hole. The only kind of other supermassive, super dense object would have to be something that is larger than a black hole. If it gets smaller than a certain size, then it forms a horizon around itself. And the way one distinguishes it is by trying to find out whether there's a horizon or not. And of course, the beautiful thing about the Event Horizon Telescope is that we have actually now seen for the first time the shadow of a horizon, and it all fits together with the Kerr metric to the accuracy of the observations, which are going to get better and better over the coming few years.
Thanks, Kip. So we don't have time for more questions. I'm sure there are many more. I have only a few of them here, but I think it's best to, at this point, to let you have a set of questions that you could answer at your leisure. And thank you again very much for a wonderful talk and taking time off from remote USA. And it's also a little bit of excitement to the talk to have someone talk from a forest in Oregon, but of course someone as distinguished as you. Thank you very much, Kip.
Thanks a lot. Thank you, Tarun. Thank you.
Okay. So after this wonderful talk from Kip Thorne, we Move on to the next speaker, who is again, is Shri Kulkarni on?
Yeah, I'm on.
Oh, okay.
Yes, he's here.
Hi, Shri. So it's my pleasure to introduce our next speaker, Professor Srivas Kulkarni, Hale Professor of Astronomy and Planetary Science at Caltech. He has also served as the Director of Caltech Optical Observatories. Shri, as most of the community knows him, belongs to a rare breed of astronomers with a remarkably keen sense to home onto the observations where a new discovery could arise. I mean, this is kind of uncanny. Throughout his stellar career, he has made many first discoveries: the millisecond pulsar, brown dwarf, extragalactic nature of gamma ray bursts, just to name a few. And of course, that has fetched him many, many awards and recognition. And I won't list all of them, but he's a fellow of the Royal Society, US National Academy of Sciences, and a foreign member of the Indian Academy of Sciences and the Netherlands Academy of Science. So Shri carried out his undergraduate study at IIT Delhi in 1978, then onto a PhD at Berkeley, University of California, Berkeley in 83, and then has been a faculty at Caltech since 1987. He has been in very close touch with the Indian astronomy community, so we have all had the benefit of his deep interest in the growth of the subject here. And personally, I met him when I was a graduate student at IUCAA when he was visiting in the early 90s. And I vividly recall the very candid and friendly discussion we had over dinner, where he narrated his own experiences as kind of a guide to what to expect. And I was just starting out on my research at that time. So it was wonderful. I've, of course, had many other opportunities. So let me now invite Shri Kulkarni to give his talk on the low cost of speculation in astronomy. And perhaps that reveals how to make discoveries. Thank you.
Okay, just to be sure, do you see my screen?
Yes.
Okay, let's see. And I want to switch. I should have done this, but ideally I'd like it to be a presenter view. Okay, do you see the presenter view?
Yes.
Okay, I mean.
Yeah, but we see a presenter view, but you would want to see it, and
yeah, that's the one I didn't.
no, that doesn't happen in Zoom as far as I know.
How's this?
This is perfect. This is okay.
Okay, good. Yeah, success.
Okay, great.
Okay, good. Yeah. So I'd like to start in some ways by apologizing to the audience for this talk, but let me justify it. Let me start with Kumar Chitray. He's sort of a theorist I always admired. He worked on interesting problems along with a great deal of class and elegance. To my, I know, of course, worked with Kumar, but I've been in touch. First time I met him was perhaps in the perhaps mid 80s. And somehow partly because I admired that sort of theory, we became close, and every time I'd go to India, I'd stop by, make a point to stop by in Mumbai, and which I've continued. In fact, the last time I was in India was February of last year, just before the pandemic started. And I did stop by in Mumbai and went to his institute, met a large group of students, and also gave a talk at the Nehru Planetarium as a part of this his institute's outreach effort. So in a way, this is to show there's that you have this researcher who does very classical and classy analytical theory on real problems. And then I want to compare that with what I consider as sort of things that are happening in our field, which some of the developments are really exciting, like what we heard from Kip. And there's some not so exciting things. And it's useful to sometimes actually step back and take a look at ourselves, at our own field. And if there's one thing I have to say to young people is there's one philosophy I always kept in mind is I'm always very skeptical of the established order. If you want to make great discoveries, never become a part of the established order. In fact, you have to be an anarchist all the time. So this is a bit of a talk along my personality, which is an anarchist. Okay, and so I would say this is probably the only talk in your otherwise excellent series, which doesn't go directly into content, which is very astronomy. But this is all about astronomy, not on astronomy. Okay, so I want to give you my views of what I consider as weaknesses in the current style of astronomy. Let's see. Okay, just a second. I'm learning how to switch here. Yeah. Okay, the structure of the talk. Speculation, it has 4 parts. One is the speculation in mainstream astronomy. Then I give you my view of structure of science. A little detour, the spectacular success of physics in the 20th century, one of which led to, I would say, now the rise of astroparticle physics, which I would say has had some problems. In particular, it has made speculative theories and models an accepted mode of inquiry. I would say it's almost opposite of how classical science is constructed. And it has led to a lot of programmatics in astronomy, which have come at the cost of exploration. And that's, to me, astronomy is largely discovery. We discover, we find patterns, and that's gives rise to the physics. So if you don't discover, we are not doing much in astronomy. Okay, but before I start blaming the physicist and everyone else, let me take a hard look at ourselves. So a couple of years ago, Nature asked me to write a review, not a review, views, since I work both in gamma ray bursts as well as fast radio bursts, my perspective of gamma ray bursts to fast radio bursts. And they in fact gave me a 2-sentence summary as what the article would look like. And it says the field of gamma ray bursts arguably went through 3 decades of growing pains before reaching maturity. What development lessons can be learned from the adolescent field of fast radio burst astronomy? So this was in year 2018. I took it up as a challenge, so I spent a couple of months. And here it is. So what I did first was to actually look at the data. Okay, and the data here, it comes in 2 forms. One is the number of papers published. We'll assume they're reasonable. The refereeing process works on the average of K. And the other citation, which is how many people are interested in the subject. So actually, this is not this is a fairly well-constructed data that I actually enjoy these sorts of programming. And so this is good data, which tells you what is the rise in, for example, this says gamma ray bursts were discovered end of 60s, and here's the slow rise of the papers in the black line. And in the dash dotted line is the excitation generated in that year, but divided by 25 so that I could fit both of them. Okay, and there are various missions here. And the reason I draw that is, for me, it's very simple. I think in my mind, the discovery is purely a matter of technology. Who happens to discover is usually more accidental. It's usually the person who happens to be at the place, with all the right things going on. So I never care much about the person, but the missions and the facilities, they make the difference. Okay, so that is for gamma ray bursts. It took a long time, but let's understand a bit of the early history of gamma ray bursts. In 1975, literally about 7 years after the discovery of gamma ray bursts, Mel Ruderman published a remarkable paper, which was essentially summing up all the models proposed for gamma ray bursts. So I'll just read a few. Expanding supernova shocks, neutron star formation, glitches, neutron stars in closed binaries, black holes in binaries, novae, white dwarfs, flares on normal stars, flare on flare stars, flares on white dwarfs, flares on neutron stars, flares in closed binaries, nuclear explosions on white dwarfs, comets and neutron stars, Jupiter, antimatter on conventional matter stars, magnetic bottles and instability in the solar wind, relativistic dust, vacuum polarization, near rotating charged black holes, instabilities in pulsar magnetosphere, and ghouls. Okay. I always find this really amazing. I mean, in my mind, the style of astronomy practiced by someone like Kumar would be, you look at a phenomena and the idea is to explain that with physics and with the plausible boundary conditions, plausible objects, plausible, locales. It's to me amazing that so many papers were written, and you know the right answer is almost all of these papers. In fact, none of these are the right answers. Okay. Anyway, so the next, from that to the basically there's a couple of red herrings from observations. It inevitable. Tremendous amount of wishful thinking, and I would say desperate theorists. Okay. The only way this whole speculative mania came down was with the discovery of afterglow, which very quickly established the energy scale, established their origin, that some come from old populations, some come from both old and new, and new, and some come from old and new, and now we know the two models of GRBs. So I sort of look at all those theoretical papers and say, what a waste of time. I mean, if I was writing papers like that, I would not feel good at all, actually. Okay, now let's move to fast radio bursts. Okay, first of all, our field has really remarkably accelerated. We have a little accelerating community here. What took 30 years to sort out is now happening on a much faster scale. There are more astronomers now. They're publishing more, they're talking to each other more. And the same scale, fast radio bursts has made remarkable progress, okay, which is all wonderful. However, some things have remained the same. In fact, there's a website that's been developed by well-meaning people, I suppose. It's called FRB Theory Wiki. Now, I actually, in the first version of the talk, I actually had about 8 pages of all the models listed in this wiki, which is a service to the community. However, I honestly don't understand the purpose of this sort of this style of research. I do remember when the Thornton paper came, and the FRBs really started taking off, there's some people saying, oh, they come from coalescing neutron stars. But it is a very simple thing. You can look at the rates, and the rates of coalescing neutron stars, and they don't match. So you shouldn't then pursue something just because you're fascinated with the idea that you like coalescing neutron stars. So I asked the person who's writing that paper, I said, why are you wasting your time? I said, oh, there may be a small fraction of FRBs which come from coalescing neutron stars. I would call that as total desperation. Okay, this is not science, in my opinion, because the proper way is you first get the first order answer. Then when you finish with that, then you get the second order answer. Okay, so I would say there's some conclusions I draw. In astronomy, my view is there's no cost to publishing speculative or even models which fail to satisfy observations at time of submission. In fact, I think if I'm a young person and a theorist, I would say there's an advantage to publishing many models on the off chance that one of them is correct. So this is like the lottery ticket thing. We all know lottery ticket is like a bad deal. But once in a while, when we get desperate, we do go and buy lottery tickets in the hope, oh, well, maybe I'll get it. But I think this is really bad science, in my opinion. And actually, it's a waste of taxpayers' money to do such speculative work. Okay, so it's not astronomers are free of fault. Now let's go to a somewhat larger picture. Let's look at the structure of science. What is science? I mean, so you could say, well, maybe that's your style, it's my style, but let's understand. The point of science is to understand the universe, okay? And science doesn't come out of pure ideas. It's not something you sit around and say, I'm going to figure it out from absolutely in my own mind. Okay, that's sort of religion at that point. Okay, and that I have a very dim view of religion because it's just a man-made thing that goes nowhere. It has actually no real value at all. In fact, perhaps in negative value. But okay, let's look at science. Science has two big steps. One is phenomenology. What is phenomenology is actually consists of discovery of what's around us. Then we do a systematic study of these phenomena, search for patterns. And once we have searched this, once we have discerned patterns, then we start developing physical models based on the physics that we understand to explain these patterns. Okay, and the point of physics. So this part here is really astronomy. Okay, the second part here is physics. What physics does is it distills phenomena into essential rules and laws. The more distillation you can do, the more successful the physics has been. And the point of mathematics from a scientist is it makes us possible to compute the signals. So let me give you an example. Anyway, for this reason, I'm a huge fan of mathematics. I think if any of you have small amount of money left at the end of your life, always give to some mathematician or mathematical institute because it's turned out to be one of the best deals we have going on in the sciences. As I already stated, my very strong hypothesis discovers a function of technology and little to do with who's there. So let me say an example of what I consider where astronomy played a key role is the development from observations, namely planetary motion were observed by ancient scientists across the sky, okay? Stars didn't move, planets moved. That's how you knew there's something special about them. With the first telescope, Galileo discovered moons of Jupiter. It immediately established, the gravitational force in some sense of things going around in a very visual way. You didn't even have to construct orbits. Brahe spent most of his life and 7% of GDP of Denmark in constructing arc-minute positions of planets. He essentially handed off the data to Kepler before, just in time before dying, who distilled that now for the first time we see patterns emerging, and those patterns are called the three laws of Kepler. Newton took the theory of gravity, the inverse square law, and tried to explain the three patterns, the three laws. But he didn't have the mathematics to actually do these orbits. So it took another 20 years where calculus had to be developed to compute trajectories and basically to solve what we now call as differential equations. Okay, that shows the central role of mathematics in modern physics, in modern science. Okay, all this finally gave rise to birth of modern mechanics. Gauss computed the trajectories. In fact, he invented the least square fit program at that point, or that's a technique, and made predictions which in fact were borne out. Okay, this is science. Observations, patterns, theory, explanation. Okay, let's look for more modern examples in astronomy of search for patterns. Let's start with a very famous example, 1A supernovae for cosmography. Okay, the astronomers didn't start off by looking at supernovae and say, oh, let's go to cosmography. Basically, astronomers started studying supernovae. They're amongst the routinely brightest events in the optical universe. Astronomers classified supernovae and patiently studied different kinds of supernovae. And after a lot of phenomenological work, it turned out, and we still don't really understand because there's no deep reason actually, that 1A supernovae are standardizable candles. So now you have a natural phenomena which apparently can be made into a standard candle, and all of a sudden you have a yardstick to go after the universe. So this didn't begin out of some grand physics program to do cosmology. This began with curiosity, search for patterns, and an accidental discovery of the constancy of 1A supernovae. Okay, another famous example, a basic goal of in the 50s, or starting at actually with Zwicky, was to determine the mass makeup of galaxies. Okay, Zwicky noticed the large velocities in clusters, and in fact proposed, and he should be given the primary credit for dark matter, that there's perhaps matter that doesn't shine. And radio and optical observations established a flat rotation curve, which was reasonably interpreted as a result for not luminous matter. Okay, So again, it was not there's a big plan to go and find dark matter, but it required search for patterns and curiosity. Okay, so now again, by the way of summary, I'll give you my view of physics in the 20th century, which is perhaps an astounding success. I think if we can go from planets to Newtonian mechanics, I would say the next major revolution was really physics in the 20th century. Okay, it's beautiful. You see Maxwell's equation, the 3 laws of thermodynamics, of course, general relativity and quantum mechanics. There's an amazing amount of physics that got done, huge progress. And finally, starting about 60s, the standard model was developed in response to new type of particles, in response to experimental data, which suggested that these elementary particles were not that elementary other than electrons and so on. Okay, so essentially the theory that was then developed to explain the then observations has not changed much, and the subject slowed down. There's nothing really much happened in all of particle physics. Probably, in the last 20 years, the biggest thing has been the Higgs boson, and you can say this is either a great success of a nice closure between experimentation and theory, but it's pretty clear at this point, particle physics doesn't have new inputs. It has many new theoretical inputs, but the fact is that no new data inputs, and without any new data, you can spin around and develop theories that you're simply wasting time. I think that's the story that we have seen with the GRB story, the FRB story, and the same thing's happening in particle physics. Okay, the success of 20th century physics had unfortunately some harmful effect, I would say. The harmful effect is that it made theoretical physics supreme, and it made it extreme. It became very fashionable to say you're a theorist. It made theory occupy a throne that is actually not very healthy for the science. In fact, there's some really ludicrous examples I can give you. For example, the classical theory of economics, okay, in particular modeling of stock market. In fact, the very first theory of financial, what we call as financial technology, was Poincare's student who applied Gaussian statistics to the price of the stock in the Paris exchange. Okay, so this continued to inspire areas outside physics, namely financial technology, so much so that the famous Black-Scholes formulation for the options, okay, these are guys who got a Nobel Prize, is based on Gaussian distribution. Of course, it collapsed, as you saw with the LTCM collapse, that the stock markets do not obey Gaussian distribution. In fact, it may be of some interest for you to know that no one actually checked whether the stock market statistics follow Gaussian distribution. It was only in the early 70s that Mandelbrot actually looked at the data, okay, and found that the stock market prices do show Gaussian fluctuations during inactive period. But when there is activity, i.e. when there's a run, okay, you get a power law, which is in the financial terms called fat tail, and which is why you have these crashes, and which is why Black-Scholes formulation is incorrect. And you have this sort of a theory-based, ideal theory-based theory model, which then actually turns out to meet reality and fail in a very bad way. Okay, now let's come back to what's happening to astronomers now. Okay, so we are now finished off all of last century. And in the last, depending how you want to look, about 30, 40 years, what the astronomers found the 3 Kelvin background, okay, not because they had a plan to go and study the early universe, but by purely as an engineering need. And I already talked of the discovery of dark matter and the discovery of dark energy. And I also hinted at, and now I can say very clearly, I think particle physicists realized, I would say by the end of last century, that progress in physics was basically slowing down in terms of accelerator physics. And there's big hopes, I would say, that maybe there'll be some really new particles as you turn down sun, and it didn't happen. Okay, that's how it is. as well as there's a natural move to, if you want to go to the highest energies, the highest density, then you have to go to the laboratory called the universe. Okay, so this mass migration of particle physicists into astronomy has given rise to a field called astroparticle physics, of which I'm a great skeptic. And the rest of my talk would be giving you my completely very clear view of this subject called astroparticle physics. Okay, I have to tell you that I'm known to actually, I sometimes think I have a sense of humor. Many of my colleagues disagree. So once in an astroparticle physics talk, it was so speculative at this point. I had to say, I have a new definition for an astroparticle physicist. It's a person who neither knows astronomy nor physics. It's in the valley between the two peaks. Okay, so what has the flux of physicists into astronomy done? It's brought in a huge cultural change, and along with that, some problems. So we now have to conceive large projects where large amounts of money are spent with rigor and metrics. But these large projects have a very narrow goal. For example, designing a whole supernova 1A survey, okay, on a mission or on a large telescope. It's an incredibly narrow goal. So here's an example. The Canada-France-Hawaii telescope undertook what was called a SNLS, Supernova Legacy Survey. The goal was to use, do a systematic study of 1A supernovae and, do the usual stuff, the cosmography and so on, which is all good. I mean, not finding fault with that at all. But they set up their filters. So the light curves had a chi-squared running, and if it deviated from a 1A, they rejected it, which was good for us, bad for them, because at the same time we were running, I started PTF, and one of the first discoveries they were superluminous supernovae, that there's a whole class of them. There's some hints of it, but then there's a whole class of them, because we were looking out for new things. And so SNLS could have found this, but they didn't. Okay, and I would call that as a very narrow view of science. So the culture has changed our subject, which is what would I call as a discovery science, to hypothesis-driven thing, which is a very big, very pet view that physicists have. But that view comes from the fact that their laboratory is highly controllable. Okay, whereas many physicists, I think, do not understand the word called false positive, and this will come up again and again. So, for example, some of the ideas of looking for cosmic gamma ray bursts, not gamma ray bursts, gamma rays from our galaxy, from decaying particles. Yeah, let's say it's even true. It turns out it's not true, but let's say it's true. But then you have to ask, are the gamma rays from other sources? And how will I know this is from this source and not from the other? It's called false positives. And astronomers are used to a very rich phenomenology. So we are very good at understanding false positives, where these large projects, some of which have spent $1 billion, only at the end of their project discovered false positives. Of course, this is all this has stopped funding appropriately to basically programs instead of curiosity. So there's a new rank order. The rank 1 is now pure theory, and there's the rank 2 has now numerical modelers, which I don't mind. I mean, I think Kip Thorne made a very good case, and I would say I was mistaken there, that of the value of numerical relativity. Mainly, I always thought if with some very clever stuff you can figure how two black holes would coalesce, but apparently not. It's a very hard problem. But there's a new group of people who are what I call experiment planners, and of course astroparticle physicists. And finally are the people who actually make the discoveries and generate the real data. And this rank matters because that's how the funding actually gets now spent. So here's my view of astronomy in the 21st century. It has now become pretty routine for most in our field. Instead of going for the simplest ideas, what is the one that can explain the most? The idea is to jump onto the most speculative one because it looks attractive. And I give 3 examples. One is designing a mission to go and find gamma rays from decaying dark matter particles. This hypothesis is unproven, is not at all proven. There's no basis for that. But there's certainly a lot of basis on saying there are other gamma ray sources in the sky. There's some electron-positron asymmetry that was seen. And within a month, there are so many papers, maybe a few hundred papers, without actually checking, maybe is there a simpler, more conventional explanation? Same thing with ultra-high-energy cosmic rays. I remember the first few I found, there's screaming papers, Lorentz invariance has been broken, there's all sorts of new physics happening. But in order to show there's something new, you have to actually show that it's breaking the old physics. I really am astonished at this departure from, what should I say, simple thinking. You can't claim big discoveries need big proof. And in order to show something big like this, you have to actually first go through all the conventional possibilities before writing papers on unconventional possibilities. Okay, and I already mentioned that. So let me give an example of where this is leading us in terms of just a second, in terms of distorting the way science is being done. Okay, so let me start with one. I'll give an example here. Let's start with the search for dark matter through galactic gamma rays. Okay, there's a project called Fermi, and if you go and look at their webpage, it says the mission in astrophysics and particle physics partnership with NASA, DOE, blah blah. Okay, the NASA goals were clear. Yeah, we'll done the sky at lower energies, X-rays. Let's go to gamma rays. That's what we should do. We're explorers. But the reason DOE put in money was to find gamma rays from a decay of dark matter. There's so many such particle physics theories now, and as soon as you finish ruling out one, there's another one that pops out. So you can't be taking all this seriously, but apparently some people did take seriously to spend nearly $1 billion. Yes, it turned out that our DOE friends did find gamma ray sources. In fact, some of the brightest gamma ray sources are millisecond pulsars, okay, very dear to me. In fact, there's maybe so many millisecond pulsars in the center here that you could not distinguish them from a decaying dark matter, even if you had one. And then the usual story that's then said is, oh, well, but then we found, so why is this not going? Oh, going the opposite. Okay. And then there's a Fermi bubble. This is usually celebrated as a great finding. Of course, it's a great finding because something very unusual that happened in the galactic center. But the number of papers which actually attribute this to decaying dark matter, to me, is astonishing, because why would anyone look at this and say, this is decaying dark matter as the first possibility? Okay, so now let me end on, in fact, a topic that segues from where Kip left. I'll take it up. And I know there's a substantial GW community in India, a GR community in India. And I very much like to imagine that in a few years, we'll have an Indian LIGO running. I'm a big fan of GR, as Kip would have told you if you'd asked him. But I'm not a big fan of all things GR community does. GR has been a stunning success in starting off with very precise tests. Okay, when you look at a diagram like this is the double pulsar. When you look at a diagram like this, you see so many constraints, and you blow up this little region, and you say, "Oh my, this is really, really nice." This means we actually understand something to the extent our data allows us to. Then there have been tests of principle of equivalence. There's been frame dragging, but of course. And then spectacular picture of a nuclear black hole. And then really the big thing is this is dynamic gravity, right? So those are tests all done at VOC much less than 1. But when you look at merging black holes, you're undertaking the strongest test of any theory, because VOC is approaching unity. Okay, that's when any theory which would be weak would start falling apart. Okay, so in some sense, this is a fantastic celebration. It's the same thing like in the particle physics things. I showed you that picture with so many particles all summarized in that one plot or one view graph, we understand the elementary nature of matter. It's really stunning. In this amazing display, we have gone from a tensor equation to actually making astronomical deductions. Fantastic. Okay, so we all know that GR is a classical theory and a quantum description is needed, no question at all. And we need some guidance to make progress. Well, it may come from experimental data, it may come from new theoretical insight, and of course, there's a huge community of people trying to unify quantum mechanics and GR. And I know I'm not a theorist, I don't have no opinion, but I'm a guy who, I only believe in success. If you're not succeeded, then I have an opinion. Okay. So let me say, okay, with all the stunning success of GR, what should observers be doing? I would say observers should continue to test GR. It's absolutely important, because if the theory is got to have any changes to make it compatible with quantum mechanics, some deviations will have to be found. Will they be found on the smaller scales, like in LIGO, or will they be found on the larger scales, like deviations from 1/r squared in astronomy? I don't know, okay, but we must continue doing this. And the observers should be looking at that chi-squared plot, like the one I showed you here. And as long as this reduced chi-squared is 1, I don't think they should in fact be bothering to talk to any theorists at all. We have a theory that's working, there's nothing more you can do. I'd do the same recommendation to the gravitational wave facilities. Fit the strain data to your model. And as Kip pointed out, during the merger, all the fun things get masked because those waves get absorbed actually. Fine, yeah, that's how life is. And publish those physical parameters, M1, M2, spin 1, spin 2, what have you, kick, reduce to chi-square, and that's it. Observers should, in contrast, I've been sitting on many time allocation committee, and then someone who wants to do precision pulsar timing will write a thing which says, there are alternative theories of gravity, and therefore we want to continue doing this. Which I think is, first of all, is silly on 2 counts. One is, there's really right now, even though I'm not a theorist, I can tell you there is really no, what should I say, actually rigorous alternative theories. I mean, theories which are actually like other physical theories. They have Lorentz invariance, they're symmetric in all the things you expect. No, they don't have. It's just many of these theories, quote unquote theories, are basically parametric expansion of something. And I even heard a talk, in the LIGO group where someone was saying, we will assume GR and then we'll allow for some additional parameters where if GR is correct, this is 0. If not, it's something. This is not really theoretical physics. This is silly. You got to find data, and the data should say, chi-squared at 100. There's no way you can fit that. And that the data should scream at you and say your theory is wrong. But to search for theories in absence of valid data, I think it just says, I would call this as intellectual underemployment. So let me end this, hopefully, a rousing talk that may get some of you all charged up. I'm trying to finish with about 9 minutes to spare so that you can get back at me with a couple of fun quotes. Eddington, I kind of like the guy in some ways and not in other ways. Asked in 1913 whether it's true that only 3 people in the world understood the theory of GR, Eddington allegedly replied, "Who's the third?" I like that spirit. But the one I don't like is, do not push too much confidence in experimental results until they've been confirmed by theory. That is silly for a guy who actually had the data in front of him, called a white dwarf, and he didn't understand that white dwarf is a natural result of quantum mechanics and gravity, even though he had all the data there. But he did leave a very interesting poem, which I'll read out. There's once a brainy baboon who always beat down a bassoon, for he said, "It appears that in billions of years, I shall certainly hit on a tune." I think this little poem expresses my view of a large number of theorists who hope to hit a tune with a large number of models. Thank you.
Thanks, Shri, for a very, very nice but very provocative talk. I'm sure there would be many people who would like to discuss this with you, but it's remarkable. I mean, I really admire the candid thing, and which I referred to in my first interaction with you as a student. And I think it's very important to put it out there for the students to take a call. I'm sure there are few questions. One is how to differentiate good science from not so good science. Is that subjective or objective? There's Amit Seta. Would you like to?
Most things in life are subjective. Okay, so it's like saying which fruit do you like the most. I think mango is the best, but if you say I like chiku, I'd say, well, I can't contest you on that. But there's one simple thing though in the end, that if you've written a paper and it's proven to be wrong, it's incompatible with data the very next day or on the day of submission or a few days later, well, it's a waste.
Yeah.
No, that you can make a genuine mistake. Okay, I don't mean like an arithmetic mistake, something that you couldn't foresee, which is why we do research, right? But if it turns out to be like writing a silly paper, that supernovae of type 1 they make FRBs, that's a real paper that I'm quoting to you. Okay, now the optical depth in this thing is so large already, it doesn't make sense. It doesn't make sense at t = 0. So the point of writing papers is to actually achieve some real progress. It's not just writing something and getting some citations. So if there's no good closure with reality, you wasted your time.
Yes, you would also agree that it's a nonlinear coupling, right? So because you have speculative theories, a lot of observational effort goes into ruling them out because people want them.
I never spent my entire career in ruling out any speculative theory, because it's very easy to come up with, the word speculative theory is incorrect. A theory should be consistent. These are just, what should I say, speculative ideas. And they have, it's sort of like have a glass of wine or whiskey. You can come up with some crazy idea. And many of these ideas that masquerade as theories or alternative theories are not that profound. And why I think, and that was my plea to us observers, don't bother answering speculative theories. They have no value for you as an observer. But maybe if you're a theorist and you want to spend your time writing one speculative theory after, quote unquote, after that, fine, good for you. But at the end of your life, at some point, you should take a stock and say, what have I accomplished?
Yes. So there's another interesting question. I don't know whom it is from, but there must be attributes that only astronomers have. And can these be applied to particle physics for good?
Well, each subject has its own, what should I say, requirement, okay? So for example, when I was growing up, I really loved mathematics. And there are a few things I could do very well, okay? I would challenge anyone to give me any integral that can be integrated, without going to the complex plane. And I could, okay, very fast, because it's a thing I liked, okay? But I realized I just don't have the skills to start understanding, heavy duty mathematics. So each subject has some demands. And the classic mistake in my mind that when physicists enter astronomy is they don't understand that astronomy is not a controlled experiment. So this is the Fermi search for gamma rays from decaying dark matter. It's a classic billion-dollar example of, I would say, naivety. Because you can say, this is my model, let me accept your model is actually a physically valid model, that there exist some particles that decay and fortunately produces exactly in the range of my instrument, around GeV to 10 GeV. The question an astronomer will immediately be asking is, are there other sources, and how would I know A from B from C? Okay, so in the same way, I think if an astronomer goes into condensed matter and does some very careful things, it may not suit well. So for example, I don't think I'd be a very good detail-oriented person. Okay, I can connect different topics in astronomy and maybe even in financial technology, but details are not my forte. So you should choose topics that map into your strengths and that you can grow those strengths into an advantage. So I always tell my students, never undertake a research in a topic unless you have unfair advantage in that topic. So saying, one of the things I tell young people in India is they say, oh, there's the usual idols in India, there's of course, Chandrasekhar, Einstein, and so on, and now Kip and so on. And it's a pity because there's so much distortion in not understanding that you may say you want to do GR and you want to do the G mu nu stuff, but if you don't have it, don't do it. And in my mind, it takes more special people to do first-rate theory, but it takes a larger number of people can do first-rate observations. And observations have a wide value. You can be a very first-rate observer and have a good knack. You can be a good person and produce a large number of catalogs and a general value to humanity. Theory has only two states. Either you're a great theorist or you're no value at all.
Okay. So there's a question which probably you would answer quickly. Would it be correct to say that the same sort of speculation, within quotes, exists in fields like string theory and quantum gravity?
I mean, this is like giving what is called red meat to a hungry dog, sort of a thing. Okay, so let's not go there. First of all, I'm not really qualified. Okay, and I wish Paddy was on this thing, because then we could have a real jousting battle here.
Okay, I'll let it go. There's another question from Professor Vivek Datar. Neutrino experiments could help in energizing the HAP experimental domain. Do you have any views on that?
Well, there's no question the real excitement in particle physics right now lies with neutrinos. Okay, I mean, there's if you can figure out the masses and sort that out, absolutely, I would not disagree with that at all. Okay, and but if I'm a young person, I would hardly be working in particle physics. I would not be. Again, I don't understand why young people don't understand. There's a simple formula in life. If you want to succeed, you have to go and do new things, and you have to look for opportunities where the growth is the greatest.
Okay. Okay.
So I won't be going at CERN and doing things. That just seems like a waste of time.
I think I don't see any further questions passed on. Of course, there must have been many questions, but
there are. Yes.
People they would be actually sending a selection of them. I would like to ask a question of my own. What is your view on machine learning and these things of where you can shift through a huge amount of data and probably make discovery, like discoveries have been made, but of course it's not human mind working on it. So do you see a potential, or do you see?
Yeah, no, I've been, the word not so much thinking is a very strong verb. I would say I've been mulling about machine learning, artificial intelligence in the following sense. So I asked myself the question in my own domain, which is, can I make a machine discovery instead of a human discovery? So let's say, as you know, I run the Zwicky Transit facility, where the world's, we're producing a very large data stream of transient events in the sky. And we're making we make discoveries by, looking at this. If you say, how do you make a discovery?
Oh, sorry, she seems to have broken off here. Can you hear him, Pratyush?
No, we can't. I think he has lost connection.
We'll get him back.
Maybe Sanved or Bhushan sir can call him if that is possible. Does he know that?
No.
He's dropped off, so he'll join.
Hello, any problem?
I think Professor Kulkarni has dropped off. So
I can join. I mean, I might. Should I start? What is
No, Sanjeev, just a minute. I think we should let Sri join back. He's not. Let's formally thank him for the talk, and we will. I know that we are running a bit behind time, but I think it would be rather unfair to not let him join back. Has anyone called him, or?
He is back. He is back.
Oh, he's back. Okay.
Can you unmute Professor Kulkarni?
There it is. Yeah, sorry. So to finish off, I know we're probably running out of time. Yeah, so we had a small group of people think, can we make a machine discovery? And it's not very clear what that means. But my view on this is we should be open to the idea that there could be
We are losing him again.
astronomical discovery.
Professor Kulkarni, can you?
Yes,
If you put your video off, maybe you can. We are losing you.
I'll turn off my video.
Yeah.
Okay. Can you hear me?
Yes, sure.
Yeah, I'm saying that there could be the possibility that we have machine astronomical discoveries, and then you could even become really imaginative. Say, can we have machine proofs of mathematical statements?
Yeah.
I think we should, these are all of our own construct, right? Mathematics is not some, I'd like to, I know one could imagine it to be some sort of a ultimate, God-like expression or something, but it's some set of logic we have developed. And once you have that, then there should be alternative ways of looking at it. So I'm actually quite gung-ho. And for the simple reason, I'm a man who, the one thing I always believe, Tarun, is simple. I'm a man with success. If you succeed, I'll admire you. If you fail, I won't admire you. It's as simple as that. Machine learning works, so let's go see how well it works. So why debate?
Okay. Thanks, Sri, again for a excellent and very provocative, but very candid talk. I really appreciate that, and I'm sure there will be a lot of discussions around it amongst the scientific community here. Yeah. Thank you again, and let's move to the next speaker. So it's my great pleasure to introduce my colleague, Professor Sanjeev Dhurandhar, colleague and as well as teacher, who's Professor Emeritus at IUCAA. Sanjeev at Bala Sanjeev at IUCAA and Bala at RRI, Bala were two pioneers of gravitational wave studies in India since the very early 1990s, when the field was, far away from sort of the kind of celebrations that you see now. And between them, they have accounted for training most of the young research community that you see in gravitational waves in India. So in the early 90s, Sanjeev's work on match-filtered extraction of gravitational waves from noisy data is recognized amongst the seminal works in the field. He has been elected Fellow of the American Physical Society and Indian Academy of Sciences, National Academy of Sciences. He's won the Firodia Award and the Medal of the Asiatic Society, among many others. The hallmark of Sanjeev's science is the rich mathematical structure and concepts he has always invoked to address sort of data analysis challenges. Okay, and here is Sanjeev, who is going to discuss another of his forays into formal mathematics to address a very knotty problem that has to do with the laser interferometric space antenna for gravitational waves, which Kip referred to and is going to be launched in the 2030s. So it's my great pleasure to ask Sanjeev to give his talk. Sanjeev?
Okay. Hello. Thank you, Tarun, for saying his kind words about me. And I would also like to thank the organizers for, it's an honor for me to be invited to give a talk in this symposium. And so I'm quite happy to do so. So should I share my screen or?
Yeah, sure.
Okay, so share. Is that there now? Is it? Can you see?
Yes.
Yes, we see it. We see it.
Yeah, it's clear. Okay. So, as I said, it's an honor for me to be, but please note that we have started this talk about 15 minutes later. So, I think I should get those 15 minutes for my talk.
Yes, sure, Sanjeev. Please go ahead.
And also another thing which I would like to say is that my laptop is a bit old and it just about takes the Ubuntu version which can support Zoom. So in the last 2 talks, the laptop has crashed 3 times. So
Okay.
it might crash in the middle, but I don't think I'm going to show anything so complicated. If there's anything complicated, it crashes. I think that's my feeling. So although the maths may be a bit complicated, but the symbols are not. So so it may be okay. But if it does crash, then I'll be back in about few minutes again, because I have to reboot and start the machine again. Okay, so let me start with the talk. So my talk is Syzygy between Hilbert and space-based detectors of gravitational waves. So you might wonder what is the connection between Hilbert. This is Hilbert, the mathematician. Okay, you know about Hilbert spaces and so on. So this is Hilbert, the mathematician, and space-based detectors of gravitational waves. And I will make it, in my talk, I will give a reference to that, what Hilbert has to do with gravitational wave detectors in space. Okay, so the next thing is about Syzygy. What is a Syzygy? So Syzygy was a word which was taken or which was borrowed from Hilbert from astronomy. So what you see in the picture in the title is a Syzygy. There are 3 astronomical bodies which have come in a straight line. So like in an eclipse, for example, if you have an eclipse, that's a Syzygy. But more astronomical bodies can come in a straight line, and then you say that it's called a Syzygy. And this word was borrowed by Hilbert in 1890, that's 130 years ago, to express something about rigs and modules, which I will talk about a bit later. Okay, by the way, this talk which I am giving here is, I have not given this talk often to physicists. Mostly I have given this talk to mathematicians, and that the audience has been mathematicians like the Indian Mathematical Society and other conferences in mathematics. So, so where I didn't have to explain too many things, but I'll keep things simple. So let me, this is a tribute to Professor Kumar Chitre. And as I've said here, welcome aboard. These were the first words he said to me when I joined TIFR as a graduate student. So when I joined there used to be a lunch. Okay, so a lunch used to be organized every Tuesday for students and faculty by Professor Narlikar. And a lot of the faculty as well as students used to be there. So I was a young graduate student in 1974 or 75. And I went for this lunch for the first time. And that is where I met Professor Chitray. And he said, welcome aboard. So that's why I remember that those words, those kind words which he said to me, where I felt very welcome into the Tata Institute of Fundamental Research. And I looked up to him for advice and guidance throughout later on. For anything which I wanted, I went to him and asked his advice. And he was very ready to give it to me. So here are some pictures which I have shown. These were taken 5 years ago with Professor Chitray. Okay, now so on to my talk. This is the first few slides are basically for students and about gravitational waves. So some of the experts might should I apologize to them. So it's a century-long wait. Einstein's gravitation. Yeah, Einstein gave his theory of general theory of relativity, in 1915, he presented his famous Einstein's equations, okay, at the Russian Academy of Sciences meeting in Berlin on November 25. In 1916, Einstein predicted the existence of gravitational waves. And 2016, 100 years later, there was a direct detection of gravitational waves, and the Nobel Prize was given to for this discovery. And it was a whole LIGO science collaboration. It was a team effort, and this was the Nobel Prize. And we have just had Professor Kip Thorne speaking in the session before this, who shared the Nobel Prize, this 270 Nobel Prize in physics. Okay, so far from the first runs, about 3 runs of the LIGO Virgo have taken place, and those are called the O1, O2, O3. And O3, there have been many detected coalescing binary events, roughly at the rate of 1 per week. And so a lot of events, black hole binaries, compact binaries like neutron stars, couple of these objects have been detected. So now, what are gravitational waves? Gravitational waves are ripples in the curvature of space-time. Here are some properties. They travel with a universal speed c, which is like 300,000 kilometers per second. They are transverse, just like electromagnetic waves. They are transverse, that means the force fields are transverse to the direction of propagation, and have 2 polarizations, again like electromagnetic waves, and they are denoted by plus and cross, and which will see why. The principle of detection is this. If you take a ring of particles, okay, so this is the picture which you get in what is called the long wavelength limit, and the size of this ring is much smaller than the wavelength of the gravitational waves. Then what you have is you take a ring of test particles, and then if a gravitational wave hits this, say with a plus polarization, then the circle gets deformed into an ellipse, then back into a circle, and back into an ellipse with the semi-major and semi-minor axis interchanged. This is for a monochromatic wave. So you take the axis of the ellipse, that's the plus. So that's called the plus. And the cross is exactly this, the other polarization, which is at 45 degrees to the previous, to the plus polarization. And any general gravitational wave is simply a linear combination of these two. Okay, with the phase difference, right, and different amplitudes. But here is for detection, there is a problem. This is the principle of detection. But in practice, this is a problem because gravity is a weak force and the waves are extremely hard to detect. And you must measure something like 1 part in 10 to the 22 in order to detect these waves. And taking into account the size of the detectors, which are huge, like 4 kilometers length, that's your LIGO and so on. So these detectors, even if they are so big and so on, with all the modern technology of holding the beams and so on, you still have to measure distances, effective distances of the size of 1,000 the size of a nucleus or the proton, you can say. So this is the thing for the detectors on ground. Okay, so now the thing changes a bit when you go to laser interferometric detectors, and there was brief mention of LISA, where I think Professor Kip Thorne in the last slide and so on. So there are these laser interferometric detectors. Okay, I'll come to that a little bit later. Here's a picture of the laser interferometric detectors on ground. The delta L is like H times L. H is the typical component of the metric perturbation, and L is the size of the detector or the length of the arm. And what you can see is that L is about 4 kilometers, and this is the detector Livingston at Livingston, Louisiana, US. This is the LIGO detector. So L is large, about 4 kilometers. It is broadband, it is scalable, and tuned to the quadrupolar nature of the gravitational waves. Okay, now I come to detectors in space. And this is the LISA project, the Laser Interferometric Space Antenna. So it's called short LISA. So we have detectors on ground, but there are limitations to that because you cannot go to low frequencies. And we have a lot of sources in astronomy and astrophysics. I mean, we have a lot of sources which emit at low frequencies. In fact, the bigger the mass, lower the frequency. And big masses, in fact, are the right kind of sources because they emit stronger gravitational waves. Essentially, the strength would scale with the mass, and the frequency would inversely scale with the mass. So, if you go to low frequencies, you expect to find a lot of astrophysical sources like supermassive black holes or things like that. So, but what is the problem with the ground-based detectors? The problem with the ground-based detectors is basically you can't go below 10 hertz. And the reason is basically how to remove the seismic noise. There is something called the gravity gradient noise and so on. There are too many noises below this in this frequency band, like clouds moving in the sky. They also produce low frequency noise. You can't do much about it. And so you cannot really go to frequencies below 10 hertz or maybe a little bit below 10 hertz. So the solution is to go to space. So the LISA project, it's a laser interference space antenna. The space antenna LISA is the thing which has been planned. And this is, you have to go to space if you want to go to low frequencies. And this is really right for students and young researchers, because I think this may be the kind of future detectors which also will be operated in maybe 15 years or 20 years time, 15 years time probably. So these are low frequency searches. They are like from 10 to the minus 5 hertz to 10 to the minus 1 hertz. They are complementary to ground-based detectors, just as you have different astronomies. You got optical and radio, optical at high frequency, radio at low frequency. They complement each other. And if you have observations at low frequencies, they complement the observations made by ground-based detectors, which are at a higher frequency. The launch so far has been planned in 2074. Here it shows a picture of LISA. It's basically 3 spacecraft which form interferometer, and it forms the equilateral triangle roughly. So 3 spacecrafts at 3 ends of an equilateral triangle. The equilateral triangle is a bit exaggerated in this picture, and this is a heliocentric orbit. That means this spacecraft go around the sun. They orbit the sun, and they are in free float. This thing. So there are such orbits where this configuration remains stable. So it's something like 60 degrees with the ecliptic. So you go to that plane and you take 3 points, and it has to rotate. The whole thing rotates at the same rate as 1 revolution per year. So this is a triangle of this thing, and this is and if you have this spacecraft, the spacecraft act as hubs for the lasers, and you can send beams back and forth between these interferometers between this spacecraft to form an interferometer, as it were in software or in space. But the problem is this is an unequal arm interferometer. So LISA is plagued by several noises, like the short noise, there's the acceleration noise, and so on, which I won't go into. The noise I'm concerned here is the laser frequency noise. Now, this noise is also there in ground-based detectors, but because you can make you can do things with the beam splitters and so on, we can adjust the length to be the same so that this noise is common to both arms and cancels. But in a space interferometer, or one interferometer in space, there the spacecrafts are freely floating, and it's impossible to keep equal distances between the spacecrafts. So what you have, in fact, is an unequal arm interferometer, and this laser noise does not cancel out. And why are we worried about laser frequency noise? It is much greater than the other ambient noise. It's few orders of magnitude greater than this other ambient noises. So let us see a two-arm interferometer which is unequal. How will you cancel the frequency, the laser frequency noise in such an interferometer? So you take, say, along one arm, it is L1. You send the beam and send it back and forth, and the phase you interfere it with the original, the light coming with the laser. What you get is the difference between these two phases, which is phi of t minus L1. I put c equal to 1, like any self-respecting general relativist, minus phi t, and so you get this kind of thing, which you can write. In fact, this is where we do this kind of thing: d1 square minus 1 acting on phi t. So d1 is a time delay operator acting on a function. So if d1 acts on phi t, it is phi of t minus L1. Now, phi 2t is similarly for the other arm, but the L1 and L2 are not equal. So if you take delta phi t, phi 1t minus phi 2t, the laser noise simply does not cancel. In fact, if they're equal, then they would cancel. But you can still cancel the noise if you send the beam once around this and once around this other arm. So what you do is you take this difference, phi 1 of t minus L2 and so on, phi 2 of t minus L2 and phi 2 of t, and then you get a thing like this, and which is 0. And so d2 square minus 1, d1 square minus 1, minus d1 square minus 1, d2 square minus 1, in terms of this, multiply acting on phi is 0. So what have we used here? We have simply used commutative algebra. This is commutativity. And d1 and d2 are called indeterminates of a polynomial ring. So this is where you get into algebraic geometry or commutative algebra. So what we have here is elements of algebraic geometry, and this is just LCM. So what I have done is we have just taken what is called the LCM. Maybe you know of LCM in school. You have done lowest common multiple. So what's the lowest common multiple? If you have 8 and 12, the lowest common multiple of 8 and 12 is 24. So because 12 divides 24, 8 divides 24. So this is exactly what we have to do. But here the ring is horribly complicated. There the ring was just ring of integers, and so even school children can do this. Here it takes really far more accomplished mathematicians to, in fact, do this kind of thing, or good mathematicians do this, or generally mathematics people. So this is called commutative algebra or algebraic geometry we enter into, and what we have is polynomials in some variables, d1, d2. Now, Lisa is in fact an unequal arm, and it's simply now the problem becomes more complicated. In case of 2 arms, it was just this. But when you have 3 arms, there are 6 beams, and you have 6 streams, U1, U2, U3, V1, V2, V3 going around, and Li are all unequal. And the current design of Lisa is 2.5 million kilometers, so which comes to like 8.3 seconds roughly. So there are 6 elementary data streams, and what you measure is fractional Doppler shifts. So this is the data that is recorded. So delta nu IT or nu naught, which is nu naught is the frequency of the laser. So what we need to cancel are this laser frequency noise, which is this Ci of t. So a data stream consists of laser beams, the C of this and so on, plus something maybe if there's a gravitational wave, optical noise, and proof point noise. And this noise is much smaller than the seeds. So what we have to do is cancel the seeds. So how can we do this? So the idea is something like what we had earlier, but now we have to look for LCM in a much more complicated set of operators. So you have U1 and U2, and I have written only the laser noise terms over here, the C's over here.
Sanjeev,
Huh?
you have about 5 minutes to leave some time for questions also afterwards.
5 minutes? Oh.
To
I
leave
have
some
hardly
time
got
for
to 20% of the talk.
Oh, okay. No, but we need to.
Yeah.
Yeah.
But I think I had about 10 minutes in the thing. But
No,
anyway.
10 minutes total, but you know,
yeah,
we have to leave some time for questions.
Okay, so the general data combination is this. So if you look at this, this is the kind of thing which you have. And you can see this is the identity, that this simply cancels the thing. So what you have is that you have something like a polynomial vector, d1, d2, d3, this thing, which acts on the polynomials over here. So now, since I have just about a few minutes or 10 minutes or something like that, I will tell you some of the solutions which are there to this. So this particular thing has to be set equal to 0. So if you look at this particular equation, this is the solution. And this is in fact the module of Syzygy's. So first talked about by Hilbert in 1890 when he talked about linear relation. That's why I talked about Hilbert there. He called it the module of Syzygy's. So if you have a general vector Pi, Qi, you have to satisfy these equations and look for operator polynomials which satisfy these equations. You do Gaussian elimination and you get this. And finally, you need to solve for the polynomials Pi and Qi. And so what you have is a solution space. The solution space is basically a null space. It is what is called the module of Syzygy's. So I'll just go through this thing quickly, that you have a homomorphism which maps this to this over here. And what you are looking at is actually is the kernel of this homomorphism. And this is called the first module of Syzygy's. And it is well known in commutative algebra or algebraic geometry. And this is what you are looking for. There's a standard procedure of how this is done. Although Hilbert did not know how to do that, but it was given by Grosvenor and his students later on. You obtain a Grosvenor basis. Then from the Grosvenor basis, you go to a module, and that is called the module of Syzygy's. And the theorems guarantee that the full module is generated. So in this case, you have a module, and what you look for is a minimal set of generators. So here is a set of generators which are here, x1, x2, x3. And another set of generators is given here, which was first obtained by Armstrong and Tinto earlier. So here x, y, z, and so on are actually delay operators, d1, d2, d3. The use of TDI is this, that you can optimally track astronomical sources. So you have a whole lot of TDI combinations, and you can change the combination just like in radio astronomy. In radio astronomy also, you can track a source by changing the phase. This is exactly what you can do with LISA. You can, for a fixed source in the sky, because the LISA moves, the frame of LISA, this goes through the frame of LISA, it looks like a 8 over here. But you must change all combinations so that it is most sensitive to a particular direction. So you can do this by using these combinations which are here. These are the minimal generators. So that's the use of this TDIs and so on. So use of TDI is this. And so results and future directions are this. We have a general method actually for all the data combinations of constant arm lengths and for cancelling the laser phase noise in LISA. So this was some of the work which we did in 2002 with Rajesh Nayak and Vinay. And we have a living review article with Vasim Tinto and myself. So methods can be easily extended to rotating LISA 6-time delay operators. And this was Nayak and Vinay. And these are called TDI 1.5. method has been applied to other space detectors with different configurations. And there are other things like the OGO, octohedral GO, which are 6 spacecrafts and so on. So this is a method which can be generally applied. Now, if you have time-dependent arm lengths, the things become more complicated. The operators become non-commutative, and a matrix approach is easily adaptable. And currently, I think these are the kind of things which are the last 2020 and so on. There are papers by Valisneri and so on. And we ourselves have posted a paper just 3 days ago on the archive showing matrix formulation are actually not different in principle from what we have done here. They are just representations of the ring. Just as you have representations of groups, you can have representations of rings, and the representations are easier to deal with in the form of matrices, because when you have non-commutative operators also, matrices by themselves are non-commutative, and so the matrix approach is easily adaptable. So matrix representations are flexible, easier numerical implementation and manipulation. So I think I'll end my talk here.
Thanks, Sanjeev. I'm sorry if I've rushed you, but are there questions? People can raise their hands if there are questions.
I can go back and explain a bit, maybe. And
okay, so yeah, so I have a feeling that given the, there are a lot of students,
yeah,
you may want to focus, on this whole idea of how to, take cue from, abstract mathematics in real problems, solving real problems. You've done that multiple times. So I feel that that might be more accessible.
Yes, I think the thing is that the basic thing was that this time delay interferometry, which is highly things in laser interferometry, that has been connected with abstract mathematics. And this abstract mathematics was thought of by Hilbert in 1890. So you can see how things have progressed from there 130 years ago in some other context, where Syzygy meant a linear relation. And there are actual methods how to do this. And by this is called the Grosvenor basis and so on for a module or an ideal. And using the Grosvenor basis, you can construct the whole module of Syzygy, which is in fact a null space. So you want a null space because it is the kernel of the homomorph. You want to map the noise to 0. That is the basic thing.
So Sanjeev, there's a question which is, on the similar lines. I mean, this is an, application of commutative algebra to something like interferometry.
Yeah.
Do you know of other such instances?
I don't know. I mean, maybe, I mean, a lot of mathematics has been used in string theory and all that, but
no,
I don't know whether,
I think people meant...
that's a different type of thing.
Yeah, they meant more to observations and,
yeah, I don't think so. I mean, here this is, see, this is a problem of cancellation of laser noise. And here what you want is, you want the same length of paths. You want 2 paths which are independent, but of the same length. And then they will cancel the laser noise. So that amounts to in this thing as taking the LCM. Okay, or the lowest common multiple. But the ring here is very complicated. It's a what is called the polynomial ring of these operators. In this case, the simplest case is just 3 variables, 3 indeterminates. And taking a LCM in this is about 1,000,000 times more complicated than the usual ring of integers which one deals with in school, where you take the LCM of whatever 8 and 12 is 24 and things like that.
So the next question you have addressed towards the end of your talk. So this was about the, even if the orbits are stable, wouldn't some perturbations cause oscillations that will result in change of the arms being a function of time?
There are things like...
and would this introduce significant noise?
Yeah, so there are things like the buffeting of the spacecraft and so on by solar, I mean, cosmic rays and things like that. But those can be, there are technologies to take care of that. And those noises are much, much less than the laser frequency noise. So it is like, but the laser frequency noise comes directly from the laser. And it is not possible to cancel it in any way. And it is few orders of magnitude greater. It's not just small. So that's the basic thing. I mean, I don't know whether somewhere in the middle, in the beginning, I have said that.
So when you have something which is a large effect that you need to cancel, are there then hardware efforts to reduce the laser noise fluctuations that you have?
Yeah, you can get rid of other noises also by this technique. You see, I mean, this is also a technique, a very simple part also has been used by radio astronomers. So where they have phase closure.
Right.
So it's something like phase closure, but much, much more complicated, I think.
Okay.
So that's the basic thing here. So the short noise, acceleration noise, and in fact, in the paper on OGO, that is the octohedral thing, they have cancelled even other noises using the same technique, using the module of Syzygy's.
Interesting. So
The Wang et
Sanjeev,
al.
Okay, so I'd like to thank you for your talk.
Yeah.
And, so also, I think it's a very interesting introduction for students to see the connections between, kind of what they would put in separate compartments of pure maths and, more, direct observations and almost like an engineering problem. And I think that CEBS being one of these places where everything comes together, one sees the value of separate departments and learning from each.
In fact, the message is the pure maths doesn't remain pure.
Okay.
It can be applied.
Right. Thanks. So on that note, let's thank Professor Sanjeev Dhurandhar for his talk. And I'll move to the last speaker of the session. Thank you, Sanjeev. So it's my great pleasure to introduce Sanved Kolekar, whom I have known as a former student at IUCAA when I was a faculty there. And he was working on semi-classical gravity with my colleague Thanu Padmanabhan. So his research has now spanned gravitational dynamics, black holes, and relativistic quantum information. And of course, I'm glad to see that he's done well. He's won the SERB Research Scientist Award recently last year, and the DST Faculty Award in 2015. And of course, when he was at IUCAA, we knew him as a SPM fellow. I should mention that as a PhD student at IUCAA, he occupied an office right next to mine. In fact, we could look at each other through our windows, and I have enjoyed many discussions with him. And I should just mention that to me, he was one of the most hardworking students I've ever come across. So much so that I used to joke that Fevicol will soon use his example as someone who is glued onto his office chair. Here's Sanved to talk about gravitational memory and quantum entanglement. Sanved, over to you.
Yeah. So thanks, Tarun, for that really kind introduction. Okay, so I'll be talking today about gravitational memory and quantum entanglement. So before I do that, let me say a few words of my reminiscence on Professor Chitre. So many wonderful things have already been said about Professor Chitre. So I would like to particularly say that I would cherish those memories with him, where we had really nice academic discussions on various physics topics, be it on black holes or on cosmology, particularly those discussions on viscous universes and models for such a universe, where we could understand the entropy of the universe. And then we also had a paper together where we discussed such a model. Of course, other than physics discussions, we also I'll also always remember the encouragement that he always used to give me, both in academics and also on a personal level, when I was in a difficult situation in my life. So I'll always be really indebted to him for that. And of course, we all miss him. And I would, I really miss him knocking on my office door during tea time, asking to coming out for chat, and then talking about various things. Okay, so with that, let me begin my talk. So this is the brief outline of my talk. So I'll be talking about, like I said, gravitational memory. Then I'll talk about what are known as symmetries. So those symmetries are known as BMS symmetries. And then ultimately how they're connected to quantum entanglement. So I'll also give a brief introduction about black hole thermodynamics. And then I'll move on to this recent claim by Hawking and company about black holes having soft hair. And after that, I'll discuss about physical processes involving some shock waves, which fall into the black hole, which have some asymmetry, and they implant these soft hairs on the black hole. And I'll apply these ideas to other scenarios, such as the Rindler trajectories in curved spacetime. So I'll basically talk about these when I move along. And then I'll connect it with the classical memory effect. So this is the classical gravitational memory effect for these kind of observers. And then I'll discuss what is the quantum version. So where I'll talk about the redistribution of entanglement across the horizon. So these are the short brief references for this talk. So let me begin by saying a few properties about black holes, perhaps which you already know, that black holes have entropy, which is proportional to its area in terms of Planck unit squared. Okay, this idea was proposed by Bekenstein in the 1970s, and it was later carried forward by Hawking with his phenomenal result where he showed that black holes emit thermal radiation with a temperature which is inversely proportional to the mass of the black hole. Of course, this is for the Schwarzschild geometry. And then these work basically propelled further research into this area, where it was shown that laws of black hole mechanics. So if you study different configuration of stationary black holes and what happens if you slightly perturb them, then it is possible to show that they are analogous to the usual laws of thermodynamics that we know. So this opened up the branch of black hole thermodynamics. And of course, in the past few talks, it has already been mentioned that black holes can only be described by, let's say, 3 parameters: the mass of the black hole, the charge of the black hole, and the spin or the angular momentum of the black hole. So this is basically the no hair theorem. We do not have any information about any other objects that have fallen into the black hole or the matter which basically forms the black hole after the black hole has formed. Okay, and other than this, the analogy between thermodynamics and black holes has been extended to the space-time properties as well. So if you look at these, so I'll just briefly tell you the gist. The references are mentioned over here. So if you look at the gravitational dynamical equations, then it is possible to show in very certain scenarios that they behave very similarly to, let's say, the Navier-Stokes equations in fluid mechanics. And other than the dynamical equations, even if you look at the nature of the action for gravity, then the action can also be shown to have a thermodynamical interpretation. So I'll leave you with that. Now let me tell you about this black hole information paradox. So as I mentioned, that black holes basically emit this Hawking radiation with that particular temperature. So the simplest statement of the information paradox is the following. So let's say you have a star to begin with, and you describe the star by defining its state. So you also have quantum mechanics along the presence of gravity, okay? And the state of the star can be defined in terms of the constituents which basically make up the star. So let's say you call that state, and that state would be a pure state. You can start even before the star has formed. So you can start from dust particles, etc. But after the star basically forms a black hole, given that it satisfies those mass limits wherein it can form a black hole. After it forms a black hole, it starts to emit this Hawking radiation. So basically it loses energy in the form of its mass. So the mass decreases. So the black hole becomes smaller and smaller. And then at the end, what you have is you would be left with this thermal radiation. Now this thermal radiation, as it happens, it cannot be represented by a pure state. It has to be represented by what is known as a density matrix. So it cannot be expressed as a pure state. So what has happened is you have started initially with a pure state, and then you have ended up with a thermal density matrix. So somewhere along this evolution, basically the unitarity of quantum mechanics has been lost. So this is the well-known problem about the black hole information paradox. So what happens to the information really that has fallen into the black hole? The ideal way to essentially resolve it is to say that, look, the outgoing Hawking radiation is not essentially purely thermal, but there could be some correlations between the Hawking quanta. So if there are some correlations between, let's say, the two particles or many particles which have come out from the black hole, then the state which describes this radiation is no longer the thermal bath. Okay, you can possibly try to write it as a pure state itself, but it is not clear where these correlations would come from. So that is the puzzle. Now let me move on to a seemingly different effect. Okay, so this is basically the gravitational memory effect. So this picture was shown, the upper part of the picture was shown by Professor Sanjeev Dhurandhar in his earlier talk. So let me just briefly repeat it. So what it says is, suppose you have this inertial test particles which are kept away far from the source. So you have flat space-time around them. And let's say a gravitational wave passes through them. So in this picture, you can imagine it is passing, let's say, perpendicular to the page. Then essentially, because of the gravitational wave, the shape changes. So you have the circle, which is basically expanded and contracted in the different directions. And after the wave has passed, let's say you look at what has happened to this system of test particles, and you would basically claim that it looks like a circle. But the gravitational memory effect, in fact, says that after the gravitational wave has passed, the original system doesn't come to its initial configuration. There would be some change in the shape. So for example, there is one particular shape which is shown over here. So this records a memory of the wave that has basically passed through it. So this is a very tiny effect, okay, and it has been basically proposed to be looked at in the future LISA gravitational wave detectors in space. So yeah, so this is a very tiny effect. Now, this we call as the displacement memory effect, because you can see that the distance between, let's say, 2 points in this initial configuration has basically changed. But other than the displacement memory effect, there is also another effect, which is the velocity memory effect. So instead of the particles just being displaced, there are certain configurations in which the particles, test particles, can also receive a kick. Okay, so there are these two different things. So this is basically the gravitational memory effect in general relativity. Now let me talk about the third thing, which are the BMS symmetries. Now we all know about the translation symmetries in flat spacetime, that if you have a flat spacetime, okay, you have those 4 translations, the 3 spatial translations, okay, in the 3 directions, and also the time translation. But what these 3 people basically discovered, Bondi, Mersner, and Sachs, that in addition to this usual translations, you have this infinite number of additional translations, which are known as the super translations, which basically leave the form of the metric. So you need the metric to be flat. And if you apply these sort of transformations to the flat metric, they leave the metric to be flat. So you have a flat spacetime, you apply this symmetry and see at the leading order whether the metric is flat. So a flat spacetime maps to a flat spacetime. Okay. So this infinite number of super translation symmetries, they are basically known as the BMS symmetries. So the picture that I have drawn over here, this is what is known as the Penrose diagram, okay, where the boundary over here is the null boundary. And if you look at the circle, you can think about that circle is basically at r equal to infinity. So it is really very far. And over there, you are making this super translation. So at every point at different angular points, you are doing a different type of translation, okay, which is dependent on the angle. So this function over here, f of theta phi, basically incorporates that super translation, okay. So this turned out to be a surprise when these people basically discovered that there are these additional number of symmetries. Initially, they thought that you should only uncover the usual symmetries, which we know, which are the translation symmetries, the rotation, and the Lorentz boost. So this was a surprise. But the interesting point is now, since we have these infinite number of symmetries, it is possible to define what is known as conserved charges, okay, by antibodal mapping. And because of that, you could have an infinite number of conservation laws. So a symmetry is always related to a conserved charge. Okay, this is from the Noether's theorem. And then when you have a large number of symmetries, you would have those many large number of conservation laws. So how does it basically connect with whatever I have said so far? So what is the connection between these three seemingly different things? So I talked about gravitational memory, BMS symmetries, and the black hole thermodynamics. So let's connect first the BMS symmetry with the memory. Now it was shown that the memory effect, which basically changes let's say distance between those test particles, that is related to this asymptotic symmetry. So if you apply such a transformation to the flat space-time at infinity, okay, it basically induces those kind of displacements in the arrangement of the test particles. So that had been shown by Professor Strominger. Okay, and this correspondence also has a third vertex. So it is also connected to what are known as soft theorems, which are connected with soft particles. So these are essentially quantum particles having zero energy, but yet they quantum mechanically they exist. So all these three things are connected. But we will be only looking at this particular correspondence and using it. Now, the third part can be connected by saying, now let's apply this particular concept of the symmetries, okay, in the context of the information paradox. So that is what Hawking and his collaborators, they basically did to claim that there are soft tests. Since you now have those infinite number of conservation charges, you can basically try to say that you don't have just the mass, charge, and angular momentum for the black hole. Now, in addition, you have this infinite number of conserved charges corresponding to those BMS symmetries. Hence, perhaps there are these correlations embedded in the Hawking radiation, which you can use to basically purify the thermal bath. And hence, the information paradox can be resolved. So that was just a conjecture. Okay, but the intrinsic question about how do these actually correlations appear in the outgoing Hawking particle, that is not clear. So let me just give you a brief gist over here. So what happened if you try to think of this Hawking radiation as, let's say, instantaneous particle-antiparticle pair creation very near to the event horizon out of the vacuum. Let's say one of the particle falls into the black hole, the other one escape outside. So they can't recombine and again form vacuum fluctuations, okay? And the particle which is basically left out, it comes to you as Hawking radiation. So that is the concept. So there is already a correlation between the infalling and the outgoing particle, but there is no correlation between, let's say, the different red arrows which you see here, which are moving outside. So the resolution of using these charges has to be thought of. So one of the ways in which we can look at how to understand these correlations is to look at this physical picture of how exactly those charges affect the your black hole spacetime. So this is again what I show here is the Penrose diagram for the Schwarzschild black hole. Okay, so this line over here, which you see, this is the event horizon of the black hole. Okay, this green line which goes inside. So this is basically our outside infinity. This green line is basically a shock wave. Okay, the shock wave has to be of a very particular form, which is known as the BMS shock wave. Once it goes into the black hole, it induces some change. Now the change is of the following type. So if you have the Schwarzschild metric before the wave, so that is the left of this region. Okay, and if you look at the space-time to the right of the wave, the space-time right of the wave has been applied that BMS symmetry. So you apply the BMS symmetry to your metric. So your metric is still Schwarzschild. So it's just a small, what we call as coordinate transformation, active coordinate transformation, or a diffeomorphism. And then you basically stitch the two spacetimes, and then you get this infalling shock wave. And this infalling shock wave basically has some spherical asymmetry. And the spherical asymmetry essentially generates non-trivial translations, because those translations are now angular dependent. So they generate different translations at different points on the event horizon. And hence they basically can perhaps retain the memory of what has fallen in, because if you have those different translations at different points on the event horizon, perhaps the Hawking particles which come out of it, they retain that particular memory because of the translation. So that was the essential idea. Now, whatever I have described in words, this is the same thing now expressed in equations. So this is basically the metric of the Schwarzschild spacetime. Over here, this function h is basically a step function. So if you just set it to 0 everywhere, you can immediately recognize, at least the GR students will immediately recognize that this is the usual Schwarzschild metric. Okay. And if you set this function h to 1, when this nu is greater than nu naught, so this is after the wave, the metric is again of a Schwarzschild, but it is just acted upon by a diffeomorphism or a coordinate transformation. Okay, and basically the h function, the step function, does the job of essentially stitching it. Now, how do we decide what are the factors which come after it? So that is given to us by the BMS supertranslation vector. So that decides us how we define this particular vector. Okay, so depending on what symmetry we apply to the spacetime, we basically define how to perturb the metric. Okay, and it is written in this particular gauge, which is known as the Bondi gauge, which satisfies certain fall-off properties. And the function C of theta, this basically describes the angular profile of the shock wave. So this tells us that the shock wave is essentially not spherically symmetric, and the asymmetry, it records about the information about the wave, and that is supposed to implant the software. So let's see how it works. So the question that we need to ask is, if we are going to see those correlations in the Hawking pairs, we should first ask which observers basically see Hawking radiation, because different observers, depending on their relative motion, they see different things. So if you have an observer, let's say, who is stationary outside a black hole. So let's say if you have a hanging observer, and if you give a thermometer, then he would see that the thermometer basically records a temperature, or if he has a spectrometer, he can plot basically the full Planckian distribution. Okay, so it is these observers who basically see that thermal radiation. If you have freely falling observers, which basically go into the black hole, then those observers would not detect the Hawking radiation. This is essentially because of the relativity. It affects the vacuum states in, let's say, a background curved spacetime. So that is another effect. Okay. Now, this particular situation which I showed you, this is very, there is an analogous situation which happens just in flat spacetime. So in flat spacetime, if you have two observers, so one is the inertial observer, so who is just at rest, and there is another observer who is, let's say, accelerating in one particular direction with some uniform acceleration, then again a similar effect is observed over here, just in flat spacetime. If the inertial observer sees vacuum, then the accelerating observer, if he has a thermometer, he will basically see a temperature, and that temperature would be proportional to the magnitude of acceleration. So the mathematics which basically goes in deriving the Hawking radiation in the case of the black holes, that same mathematics or the same techniques or the same concepts, it basically also works in the case of this situation. So this radiation is known as the Unruh radiation, in the name of the person who first discovered it. So what we are essentially going to do is, instead of working first with the black hole situations where things look complicated, we can try to understand what happens in this simpler case. Okay. So over here, we would try to ask, so this is basically the space-time picture of those accelerated observers. Again, the GR student would recognize this as the familiar picture, which is discussed in their GR course. Okay. So, and these are the corresponding Rindler horizon. So this is the future horizon, and this is the past horizon. And this is, of course, the hyperbolic trajectory is the Rindler trajectory. Okay. So the question we need to ask is, once this shock wave basically passes, now we are in the flat space-time. So if the shock wave basically passes, what happens to this family of Rindler observers or the uniformly accelerating observers? How are they basically affected? So studying this would tell us about the classical memory effect. So in the earlier case, we had inertial observers in the usual gravitational memory effect. Now we are trying to study the gravitational memory effect on the class of uniformly accelerating observers. Okay, with the motivation that we need to understand what happens to the Hawking radiation, because these observers are the one who would detect the radiation. So again, what we do is we have the BMS symmetry in this particular situation. We have the shock wave, which basically stitches two parts of the Rindler spacetime. Okay, one is the usual Rindler spacetime, and the other is the symmetry applied Rindler spacetime. You stitch it and then you understand. Now, there is one issue. Writing freely falling observers in curved spacetime is easy because we know that the equation which describes those is basically the geodesic equations. Okay, but how do we define uniform linear acceleration in the presence of curved spacetime? Now remember that since there is a shock wave over here, the shock wave basically has a energy momentum tensor. So at that particular location, you would have non-zero curvature tensor present. So it's not a complete flat spacetime. Okay, it's a flat spacetime except at the shock wave. Okay, so you need to basically explain what happens to this uniformly accelerated trajectory once they pass over this shock wave. So that is where this construction about let's say the Ferret-Serret equations, which you have studied in your let's say Euclidean geometry, the same concept would help us. So here we basically say that let's define a linearly uniform accelerated trajectory to be such that it is moving in a plane, because that is what the Rindler trajectories they do. They do not have any kind of rotation or a twist in the trajectory. Okay, so we use the concept about the Ferret-Serret equations, and then if we apply these to that concept to this particular trajectories, then we can define what are linearly uniform trajectories. Okay, and once you do that, then you have now three type of scalar quantities. So usually you would only have the curvature scalar and the torsion scalar, but now since you are in the four-dimensional spacetime, you also have the hypertorsion. So the way to define planar trajectories in this case is to say that there is no torsion or hypertorsion. So that would take care of the rotation or the twist being zero. Okay, and the curvature scalar is then related to the acceleration of the uniformly accelerated observers. So once you do that, you arrive at the constraint which you must impose, which is given by the form over here. So it essentially says that any change in the force velocity of the observer or any change in the for acceleration vector for the observer as it moves along this own trajectory must lie in the same plane, the plane generated by U and E. Okay, so that is the constraint that we go about. So essentially, what is the physical picture that we get? Okay, the physical picture is the following. So if you try to look at closely over here, you can always construct a local inertial frame over this particular wave. In that local inertial frame, the construction ensures that your hyperbolic trajectory is also locally hyperbolic when it basically passes over this wave. Okay, that is what the construction guarantees.
Sorry to interrupt, but you need to wrap up in a few minutes now.
Yeah, so I'll finish in 5 minutes, 5-6 minutes.
Okay.
Yeah. So applying this set of equations, what we essentially find is that the trajectories, when they pass over that particular wave, they essentially get a Lorentz boost. So in simple terms, they basically get a kick. So now they are lying in one plane. Once they pass over the wave, get basically a transverse kick. So they can move in the Y and Z directions. And the nature of the kick basically depends on this aplanar function which we introduced in the wave. So there was a function f which basically described the aplanar symmetry of the wave, and that decides what is the amount of kick that the that a particular trajectory would get. So different observers would get different kicks depending on where they basically are affected by this aplanar trajectory. And that is essentially the classical memory which is retained by this passing shock wave. Now, this was about the classical case. Next, we talk about the quantum case. So to understand the quantum case, I'll just repeat the Unruh radiation, what I described before, now in terms of this set of equations. So this is basically the vacuum state which you see here, the vacuum state as seen by the inertial guy. So let's assume that this t-axis is actually the trajectory of a inertial guy who is at rest. So to him, if he says vacuum, which is described by the state in the left-hand side of this expression, the state which is seen by the observer who is uniformly accelerating, so the trajectory which I marked R over here, to him, he will basically use this state and then trace over all the degrees of freedom which are hidden to the left, because these two wedges are basically causally disconnected. So any observables which depend on the degrees of freedom to the left wedge, they are not affecting any measurements which happen in the right wedge. So if you do that tracing, you essentially end up with this thermal density matrix, and that is what this right side observer will do. Now, our question is what happens to this particular state when that shock wave essentially passes? So that will tell us that the entanglement between the left modes, which is denoted over here, and the right modes over here, how it changes. Okay, so the physical picture is this. So initially, let's say I have plotted here red arrows. So initially you have entanglement between, let's say, a particle A on the left side with the particle B on the right side. There is entanglement between them. And similarly, there is another pair of particles C and D with entanglement between them. The question we want to ask is what happens when this wave passes. Okay, initially there is no cross entanglement. So the blue arrows and the red arrows, they do not have any entanglement. Okay, neither B is entangled with D. Now the question is what happens when you have this BMS shock wave, which basically passes. Okay, so we basically solve the field equations in this presence of the shock wave. We basically stitch it appropriately, solve the situation, and then what we essentially find is depicted over here. So we essentially use the entanglement monotone of negativity to compute the negativities between those two particles for the state that we had. And initially, the initial negativities are summarized in this column in this table. So before the wave, that is nu less than nu naught, only A and B are entangled. Okay, there is no entanglement between BD and BC. But after the wave has passed, what we find is there is an entanglement generation between B and D, and that is that is basically of linear order in some perturbation parameter. And there is the entanglement degeneration, okay, between A and B, which is of order lambda square. Okay, and yeah, so this is essentially the way that we want the results to proceed. So because of this particular symmetry, because of the memory effect, the entanglement is basically redistributed. So how does it behave when you have Schwarzschild black hole present? So in the picture of the Schwarzschild black hole, it essentially says that if you have this infalling Hawking particle pair A and the outgoing Hawking particle B, they have entanglement between them, and you have another pair C and D, they have entanglement between them. When the shock wave basically passes, it generates entanglement between B and D. So these are the outgoing Hawking particles. So essentially now correlations have been generated in them. Now this whole calculation is basically a perturbative calculations to linear order. So much is still left to be done, and there are other interesting effects which also would come if you look at the higher, or if you ask what are the higher order corrections involved. And as a passing by, I will also mention about the quantum monogamy relation, which says that if two particles are maximally entangled, then there is a restriction which is put by this quantum monogamy relation, which says that at the most this particle B can entangle with the third particle is restricted. Okay, now it would seem that the entanglement degradation goes to order square in perturbation, but the generation is of order lambda. But the bottom line is we have worked out the technicalities, and it works very nicely to the linear order, that there is no harm to this quantum monogamy relation, and it is still valid. So the entanglement distribution in such a way that we still have the this quantum monogamy to be conserved. Okay. Now, of course, whatever we have done here so far, it can be also applied to a much general case and asked what happens. You can ask the question whether motion also affects entanglement. And the techniques that we have developed can also be applied to these cases. But since we are short to time, I would just leave you with that and ask you the question that if there are in general two entangled particles which are moving in a background curved geometry, how does the local curvature affect the entanglement between them? So that is the most broader question that is interesting to be basically addressed. Okay, so let me stop here by just mentioning the summary. So I have talked about three things: the black hole thermodynamics, the BMS symmetries, and the gravitational memory. Then I have connected all of them and shown how it can be connected to the black hole information paradox. Of course, the results which are mentioned here, we do not claim that it's a resolution of the information paradox, but at least it is suggestive that pursuing this idea further could help us to understand more about how does the entanglement gets redistributed along such things. So with that, I'll stop here. And
thank you, Sanved. So I'm sorry to be rushing you, but I hope to finish before giving a gap for people at least till the next session. Thanks. It's very intriguing, work that you've kind of described here, and I'm sure there will be a lot of questions from youngsters as well as probably others. But let me read out a few quick questions, and please, try to see if you can give a quick answer. So, does the expression for thermal radiation remain inversely proportional to mass when applied to metrics more complicated than the Schwarzschild metric?
Yeah, so if you have other kinds of black holes, let's say the Kerr black hole, then what comes in that formula is essentially the surface gravity. So the surface gravity at the event horizon is what tells you the temperature. So the temperature is proportional to the surface gravity. And in the Schwarzschild geometry case, the surface gravity is inversely proportional to the mass. So in the case of Kerr black holes or any other charged black holes, the surface gravity would also depend on the charge and the spin, etc. So the formula would get appropriately modified.
Thanks, Samved. What would initiate the shock wave in Schwarzschild black holes?
Yeah, so what we considered is an infalling shock wave. So, so this was essentially an in-principle calculation to basically stitch the two different parts of the space-time, one with the usual form of the metric and the other where we applied the symmetry. So yeah, so that would be like sending a very particularly designed shock wave which respects that BMS symmetry into the black hole.
Okay, so the third question is, what is the source of memory of gravitational waves? What entity could possibly store that memory? This is from Pratyush Bhatnagar. The previous one was from Prithvish. Prithvitosh. Okay.
Okay. So yeah, so in the displacement gravitational memory effect, the memory is stored in the configuration. So I showed you that ring of test particles, and you look at the shape of the ring of test particles after the wave has passed, and you check whether the distances between the different test particles, whether they remain the same or they are different. So in that sense, you can basically check whether they have retained a memory. So that in itself is a detector to detect the memory.
Thanks. So I think you will have a chance to answer these students offline too, because they're your students, I guess. And so thanks again, Sanved, for a nice talk. And I think it's time to close the session. And I would like to thank all the speakers of the session and hand it back to the organizers. Thank you.
Thank you, Professor.
Thank you, Professor Souradeep. It's very kind of you to spend time with us and sharing this session. I think we'll have a very short break because we are already running late. So we'll again meet at the scheduled time around 12:15, and we'll come back.
Thank you.